Hello there, and welcome to this course on Spring Transactions. In this comprehensive course, we will dive into the details of transaction management, starting with the fundamental basics, exploring the essentials, and learn how to manage transactions directly on MySQL level. From there, we will advance to more complex topics by focusing on how to manage transactions within the Spring framework. We will cover a wide range of topics, starting with a deep introduction to Spring Framework, declarative transaction management, logging and debugging transactions, exception handling, managing rollbacks, taking the event-driven approach using event listeners and the transactional event listeners, transaction boundaries, recovering from failure, isolation levels, programmatic transaction management, automated transaction testing, and much more. This course is designed to be highly practical. We will start from scratch with an empty Spring Boot project and develop a fully functional backend for our food ordering app. Our application will handle creating new categories, editing existing ones, and remove categories when they are no longer needed, managing our product listing by adding and removing products from the selected category, placing new orders, and handling the checkout process. During checkout, our backend will deduct from customers' balance, simulate generating invoices, and sending emails. At first glance, our project may seem simple, but by implementing these features, we will explore different scenarios for using transactions, providing you with the practical experience needed to start using transactions in your own project. So, who am I? My name is Hussein Akar, and I'm a full-stack engineer with over a decade of experience. Throughout my career, I've seen many projects face challenges and even fail due to lack of understanding of how transactions actually work. That's why I decided to create this detailed and practical course to share my knowledge and experience with you, helping you avoid unexpected issues and eliminate those long debugging sessions trying to understand why transactions aren't working as expected. We will do that by really understanding how transactions work and how to implement them properly in real-world projects. Join me on this exciting journey and let's explore the world of Spring transactions together. Hey, before we get started, let's make sure you are all set to get the most out of this course. First, you need a basic understanding of Java. We will be doing a lot of coding in Java, so make sure you are comfortable with the basics, like creating classes, writing code, and calling methods. Next, it's helpful to know a bit about MySQL. We will be using MySQL database throughout this course. If you know how to create tables, run queries, and manipulate data, you will find it much easier to follow. Lastly, we will be using the Spring framework for pretty much everything in this course. If you're already familiar with Spring, that's great. But if you are new or need a refresher, don't worry. In the next section, we will cover all the basics and common terms to make sure you are ready to take this course. Here, how to navigate this course. Make sure to follow the videos in the order they are presented. The only optional section is the Introduction to Spring Framework section. If you're already familiar with Spring, feel free to skip it. Pause the video if you want to take notes or code along. Use the playback buttons to slow me down if I'm going too fast or speed me up if I'm going too slow. If a concept is not clear, make sure to watch that part again. The best way to learn is by doing. I encourage you to code along with me. Don't just watch the videos. Write the code, debug it, and make sure it's working as expected. Each lecture has the starting code attached. You should be able to follow along without it, but you can use it if something isn't working or you need to compare it to your code and troubleshoot any issues. Don't forget the Q&A section. If you have any questions or something isn't clear, Ask away. I will make sure to respond within 1 day. Now that we covered everything you need to know, let's get started. See you in the next section. Glad you are here. In this module, we will dive into the details of Spring Framework to get you ready for mastering the Spring transactions. By the end of this module, you will have your first Spring Boot project up and running, capable of handling CRUD operations, creating, reading, updating, and deleting data through API calls. This will give you the practical experience needed on how to build three-layered architecture and how to interact with MySQL database. We will start by exploring what is the Spring Framework and why it's so important in Java development. Next, we will dig into fundamental principles like inversion of control and dependency injection and how they make the Spring Framework so powerful. After that, we will check how Spring manages beans and how annotations make our life easier by simplifying the configuration. We will break what each of service, repository, and controller stands for and how they work together in Spring application. At the end, we will put all that theory into practice by building a simple Spring Boot project that integrates everything we have covered in this module. So, if you're already familiar with these topics, feel free to skip to the next section. But if any of these terms sounds new or you need a quick refresher, you are in the right place to build the solid foundation needed to take this course. See you in the next lecture. What is the Spring Framework? Spring is a powerful, feature-rich framework originally created to support the development of Java Enterprise Edition applications. However, since then, it has evolved to much more than that. Nowadays, it plays a crucial role in developing enterprise-level applications. It offers an extensive range of functionalities that simplifies configuration, managing databases, and conducting comprehensive testing. It also facilitates the integration among various components within our application. To truly understand the importance of Spring Framework in Java development, let's take this practical scenario. Consider we are building a simple application where an order service needs to communicate directly with an invoice service. In traditional Java development, we could consider creating a new instance of the invoice service inside the order service constructor. This approach is straightforward, but it has drawbacks. It can lead to creating multiple instances of the invoice service, which is not great for performance. To address this, we could design the invoice service as a singleton. This design ensures that the entire application shares a single instance of the invoice service. To achieve this, we make the constructor private to stop other parts of the application from creating new instances. We then establish a static variable to hold our single shared instance. Finally, we implement a method that allows other services to access this instance. If this instance doesn't exist, we create it. Otherwise, we return the existing one. Next, we need to update our order service to utilize the getInstance method. This solution sounds better. However, there's more to consider. What if multiple parts of our app tried to access the singleton at the same time? Suppose thread 1 and thread 2 checked if the instance is null, finding it to be true. Then each thread could end up creating its own instance, and we would face the problem of multiple instances again. To avoid this and ensure one instance is created, even in multi-thread scenarios, we use the synchronized keyword. It will ensure that only one thread can create the instance at any given time. Using the synchronized keyword on our getInstance method help prevent creating multiple instances, but it also comes with drawbacks. It can impact performance, as threads might be blocked while trying to access the getInstance method at the same time. A more refined approach would be adding the synchronized functionality inside the method. This way, if an instance already exists, there's no blocking. We then double-check to ensure no other part of the application created another instance in the meantime. This approach minimizes the waiting time and keeps the application running smoothly. Managing this complexity for every service in our application isn't easy. Luckily, there's an even more efficient solution using what's called static holder. This technique leverages Java mechanics to ensure our service is thread safe and lazily loaded, meaning it's created only when needed. Even with our invoice service neatly handled, our order service still has a lot to manage, especially how to correctly initialize the invoice service. So what will happen if our application grows and now our order service need a payment gateway and a notification service? Things get even trickier. The payment gateway depends on a payment validator, and we need to support communicating via both email and messages. Managing all these dependencies manually can quickly become impossible. This is where the Spring Framework shines. In the next lecture, we will delve into dependency injection, one of the most critical features in the Spring Framework, which is capable of handling complex dependencies, making the process much more straightforward. See you in the next lecture. In Spring Framework, two key concepts that makes development much easier are dependency injection and inversion of control. They help in manage large projects and reduce the direct dependencies between components. So, what is dependency injection? Dependency injection is a design pattern that manages the object dependencies. Instead of a component creating its own dependencies, dependency injection allows them to receive these dependencies from external source. For instance, if we take our previous example, our order service had to know exactly how to create a new instance of the invoice service. But with dependency injection, that isn't a requirement anymore. In simple words, dependency injection allows a component to receive its dependencies instead of creating them. But there's still something missing. Who is creating these dependencies? That's where inversion of control comes to the picture. Inversion of control is a principle where the responsibility of creating and managing the life cycle of an object moves from the developer to the Spring Framework itself. This shift means that Spring will manage the whole life cycle and the creation of objects, letting the developer focus on the business logic. Whenever a service needs a dependency using dependency injection, it will receive that instance from the inversion of control container. Spring will use application context to get that instance. Spring offers multiple ways to implement dependency injection, using constructor injection, setter injection, or field injection. The constructor injection is the most recommended way. It will make testing much more easier. Now that we have a basic understanding about dependency injection and inversion of control, let's revisit our previous example and implement dependency injection. We start by marking the invoice service with the add service annotation. This way, we inform Spring that it should manage this class. Don't worry about the add service annotation for now. We will cover it in the next lecture. With Spring now responsible for our service, we can simplify our code by removing all the code responsible for creating a single instance of the invoice service. We need to add the same add service annotation to the order service and inject the dependency directly to the constructor. With this change, now Spring is managing both our services and is capable of passing the correct instance to the order service. So let's write a test and validate we can get an instance of the order service using the application context, and then validate that this order service has an instance of the invoice service. Don't worry about all the complexity around this class. Just focus on this application context where we get a new instance of order service. Then we validate if that order service has a valid instance of the invoice service. As we can see, our test is green, and that's confirm that Spring was able to manage our beans and get us the correct instances. A quick side note, once a class is managed by Spring, we call it Spring Bean. That's why in the application context, we used the getBean method. In the next lecture, we will dive into creating our own annotations and check how Spring uses annotations to simplify configuration and manage beans. See you in the next lecture. Annotations in Java serves as a form of metadata that provides additional information to the source code, compiler, or runtime. These annotations are declared using the symbol preceding a Java interface. They can be applied on various program elements, like classes, methods, fields, and properties, allowing developers to embed additional information directly to the source code. In Spring Framework, annotations play a crucial role in component scanning, configuration, and mapping beans. Spring offers multiple annotations that help us register a class as a Spring Bean, and each one have a specific purpose. The add component annotation is the most generic one, and used when no other annotation precisely fits the purpose. The controller annotation specifies a class as MVC controller, enabling it to manage web requests. Add service marks the class as a service component within the business layer, indicating its role in executing code related to our business logic. Repository annotation specifically tailored for data access and persistence tasks. This annotation is used when Java classes interacts with the database. Bean annotation is unlike the others. It is a method-level declaration that offers a greater control over the bean creation and configuration. Let's put theory into practice and create our custom simple logging annotation that's responsible for creating a log before and after a method being executed. We will start by creating annotations package and place our simple logger annotation in that package. We need our annotation to be executed on runtime, so we will have our retention policy set to runtime. As we know from before, annotations can be executed on classes, methods, properties, and fields. In our case, we need to place our annotation above a method, so we will define a target as a method. Our annotation is ready to be used. Let's navigate to our order service and create a simple createOrder method that simulates creating new order by just logging to the output. Then place our custom annotation above that method. Now let's write the implementation of our annotation. We will start by creating a new class and name it Simple Logger Aspect following the Spring convention. Our class will contain two methods, the before and after methods. Each method will write a simple text to our output. Let's navigate back to our order service test class and create a new method. As before, we will create a new instance from the order service using the Spring framework. After having the new instance, we will simply call the createOrder method. In the console, we should have 3 logs, 2 logs coming from our custom annotation executing before and after the actual method execution. As we can see, annotations make it easy to add extra functionality to our code without the necessity to touch the original code itself. With this basic understanding of the Spring framework, we are ready to create our first Spring Boot application where we can apply and practice all the concepts we have covered in this module. See you in the next lecture. Today, we are going to build our first Spring Boot project from the ground up. Spring Boot makes development much more easier by providing auto-configuration and an embedded Tomcat server that allow us to have a running application within minutes. First, we need to create a Spring Boot project. And what an easier way than firing our browser and navigate to start.spring.io. Once we land on the Spring Initializer homepage, we will see a huge set of options awaiting for selection. Don't worry, we will navigate through this together. Let's start by choosing Maven as our project type. Next, select Java as our programming language. Now, it's the time to check the latest Spring Boot version available. In the project metadata section, there are a few fields to fill out. The group represents the base package for our project. Let's customize it to something like com.project. The artifact serves as a unique identifier for our project. For this project, I chose First Spring Boot Project. As for the project name, let's keep it as it is. For packaging, let's stick with the jar. This way, we can package our project as a standalone jar and run it anywhere. Choose the Java version that matches what you have installed on your machine. I am currently using Java 21, which is the latest long-term support version at the time of recording. A quick note, whenever we use Spring Boot 3 or above, Java 17 became a minimum requirement. For dependencies, we are building a web application, so let's have Spring Web our only dependency for now. Let's hit the Generate button and the magic happens. Spring Initializer generated a project for us faster than we can imagine. After downloading our project, open up your favorite IDE, whether it's IntelliJ, Eclipse, or any IDE of your choice. I am using IntelliJ for the entire course. Let's unzip our downloaded project and import it into our IDE. Now, it's the time to reveal the power of Spring Boot. Even before writing a single line of code, we can fire up our project and get a server running. Either by using the Run button from the top or by using the terminal by entering the command mvn spring-boot:run. Spring Boot has launched a server for us. Our Spring Boot application is up and running on port 8080 as shown in the console. Let's fire up our browser and visit localhost 8080. We will encounter a white label error page, which basically means that the server is up and running. To confirm that our server is running, let's try a different port, like 8085. We got an error message saying this site cannot be reached. That's the power of Spring Boot. We were able to run our first web application without writing a single line of code. Congrats on having your first Spring Boot project up and running. See you in the next lecture. Hello. We want our server to handle requests coming through API calls. So let's dive in and create a controller. To keep things organized, we will create a package called controller within our base directory. Inside this package, we will place a class called user controller. We will annotate our class with the @controller annotation to declare it as MVC controller ready to handle requests coming through API calls. Also, we need to specify the path this controller will handle. In our case, it's the /users endpoint. That means whenever a request is directed to localhost 8080/users, Spring will try to handle that request using this controller. Within our controller, we will create functions to handle various CRUD operations. We will start with the getUsers method. It will return a string for now. We need to annotate our method with the @request mapping so we can define additional path and specify if it's a get, post, put, or delete request. In this case, it's a get request because we are fetching the user data. We also need to add the @response_body annotation to make Spring aware that we are not returning a view. Because we are using REST API calls in our controller, we can simplify the code a little bit by replacing these two annotations by a get mapping annotation and replace the controller with @REST_controller. This way, Spring will automatically handle serializing our response into JSON and make the code a little bit simpler. Let's return a simple message so we can test if the controller is working as expected. Let's start the server using the run button or using the command line with mvn spring boot run. From our browser, let's navigate to localhost 8080/users and hit enter. Spring was able to route our call to the correct method. Back to our IDE, let's return list of users instead a string. To do that, we need an object that represents the users. In our case, we call it a domain. Let's create a user class inside the domain package. This class will have 5 properties: the ID of type long, and first name, last name, email, and password of type string. In our controller, we will create a list of user variable to hold our data for now. In the constructor, we will instantiate our users variable with a new array list. And let's add a new user of ID 1, first name as user, last name as 1, a creative email like user1@mail.com, and 1234 as our secured password. Let's replicate user1, changing the ID, last name, and email. Now our list is ready to be used. Let's change the return type. In Spring Boot 3 and above, it's possible to return the list of users directly, whereas with older versions, wrapping the response with response entity is required. Let's return a new response entity wrapping our users list. Back to our browser, let's refresh the page, and we should get a JSON value representing the 2 users we added to the list. It's time to create our second method, which will fetch a single user using the user ID. We will create a public method that returns a response entity of type user. Let's call it getUser. We need to add the get mapping to allow Spring to map this method, and we need to include the ID as part of the URL, which we call a path variable. To access this variable, add the path variable annotation as a function parameter. Let's map it from the ID as we called it in the get mapping, and we can give it a different variable name to be used within Java. Let's use Java streams to filter out the list and get the user with the ID matching the one we got in the path variable. We will find the first match assuming our users' IDs are unique, and we will return null in case there's no match. As before, we will return a response entity wrapping our variable. Let's restart the server and test our API. In the URL, we will add /1 to get the details of the user with ID 1, /2 to get the second user, and if we try with /3, we will get null, which will display nothing as expected. We are able to fetch the list of users and a single user by ID. Let's add a method to create new users. But we need to retrieve data from the API. So we need to create an object that represents the incoming data. This class could be named as payload, DTO, bean, or anything indicating its purpose. I will call it user payload, which will have fields similar to the entity but without the ID. Let's generate getters to get access to these properties and go back to our controller. We will have the create user method annotated with the post mapping annotation to indicate it's creating something that doesn't exist. In the method parameters, we will use the request body annotation indicating the user payload as our request body. Let's start by creating a new instance of the user. For now, we will get the next user ID by fetching the max ID from the users list or set it to 1 if not found. Let's map the fields from the payload to our user's entity and add it to our users list. Let's return a new response entity wrapping our newly created user. Before we proceed, I believe you're already aware that our code has a bug. We missed incrementing the ID by 1. For that, we will set the default as 0 if the list is empty and always increment that value by 1. We will restart the server to apply the new changes. To do a post call, it's not possible using the browser. Instead, we need an API tool that allows post requests like curl or postman. I will be using Postman for the entire course. If you don't have Postman installed, you can follow the instruction on its official page. After installing Postman, let's create a new collection and give it a name. In our new collection, we will start by creating a new request of type GET that calls http localhost 8080/users. After hitting the send button, we should get the same values we got in the browser. Let's give this request a name and proceed to create the getUsers request by adding another get request to our collection that calls the /users API followed by the user ID. Let's send the request and we should get a response with details of user with ID 1. Now that we know how Postman works, let's create a post request by adding a new request to our collection. This time, the type should be post with the /users endpoint. In the body section, we will define the body type as JSON. It will include a first name, last name, email, and password. Then let's send this post request and we should get a response indicating that the user was created and added to the list. At this point, we are able to get and create users. But what if we need to update them? For that purpose, we will create a new method with the put mapping annotation, indicating this API will update existing data. Let's pass the user ID as a part of the URL as we did with the getUser. We will return a user directly without wrapping it in the response entity to show it works fine with the Spring Boot 3 and above. Our update user method also have a request body holding the updated data. To update a user, we will try to fetch it from the list and throw an exception if that user doesn't exist. If we try to update the user properties, we find out we are missing the setters. So let's generate them quickly, skipping the ID, because once the user is created, we shouldn't be able to update the user ID. We will set the user properties to match the payload values and simply return a user. Spring will handle wrapping our user with a response entity. Don't forget to restart the server, then head back to Postman. We will create a new user, then update the password. Let's generate a new user as before and get the all users to confirm the current data. Then let's create a new request with the type put and the same URL as before. Let's try to update the user with ID 3 and it should have a JSON body similar to what we have in the post method. Let's copy and paste the body and update the password from zeros to 1234. Let's send the request and use the getUsers API to confirm the data was successfully updated. It's time to add the last member of our CRUD operations. We will start with a public method that has a response entity of type void to indicate it shouldn't return a value. Let's call it deleteUser and have the user ID as a path variable. Next, we will annotate our method with the delete mapping annotation and have the ID as part of the URL. To delete a user, we will start by fetching that user from the list as we did in the updateUser method, and simply use the .remove method to delete that user. After that, we will return a new instance of the response entity with the HTTP status of no content. Let's restart the server and create our final API in Postman. This request will have the type delete and call the endpoint of users / the ID of the user we want to delete. After sending the request, let's use the getUsers API to validate that the user with ID 1 does not exist. We successfully created our first layer of our 3-layered architecture. Our controller is able to handle basic CRUD operations, and we know how to do that using Postman. But our controller is doing a lot of things, and they are not the controller's responsibility. In the next lecture, we will introduce the service layer and move all the business logic to that layer. See you in the next lecture. Our controller is ready, but it's taking more responsibilities than it should. It's time to introduce a service layer that handles our business logic. Let's start by creating a user service interface under the service directory. This interface will be implemented by a class called userServiceImpl in the impl package. We will annotate our class with the @service annotation, so it got registered as a Spring Bean, indicating its purpose of handling business logic. From the controller, we will move the user list creation and instantiation to the service layer. To instantiate the service inside the controller, we will depend on Spring in version of control container to do that. All we need to do is inject the user service bean into the controller's constructor. After removing the unnecessary code from the constructor, we will begin with the getUsers method. This call will be delegated to the service using a new method called getAllUsers. This method will be generated in the user service interface and implemented in the userServiceImpl class. Our method will return the users list as it is. To test our changes, let's run the server and navigate to Postman. Let's trigger the getAllUsers API and validate the response matching the previous results. Next, we will refactor the getUser method. We will delegate this call by creating a getUser method in the user service interface that takes user ID as a parameter. We need to implement this method and then paste the logic from the controller and update the variable name from ID to user ID. We can also inline the variables by returning the stream results directly. Let's restart the server, and from Postman, let's fetch the details of user with ID 1, ID 2, and non-existing user. The responses should remain consistent with previous results. For the createUser method, we will create a new user variable and assign it the value of userService.createUser. Let's cut the existing code from the controller, create the method in the interface, and implement it in the service. We need to modify the method to return user instead of null. Once refactored, let's restart the server and use Postman to send the request. The response should include ID 3 indicating the successful creation of our user. Similar refactoring applies to update user method. Let's cut the code and create a user variable and assign it to the user service.updateUser. It takes the ID and the payload as parameters. Let's create the method, then implement it and return a user instead of null. Back to our controller, we can inline the variable by returning the service result directly. We will proceed by refactoring the deleteUser method by cutting the existing logic from the controller, delegate the call to the service, and implement the method. We need to paste the code to the newly created deleteUser method and update the variables. Let's restart the server and switch to Postman. We will update the user to last name, email, and password, and verify the changes by calling the getUser API. Finally, let's delete the user and ensure it has been removed from the list. As we continue building, we are getting closer to the architecture of enterprise application. However, our service layer still know about the data, which should be the responsibility of the data access layer. In the next lecture, we will introduce the repository layer, completing our three-layered architecture. This will ensure that our service layer will focus only on the business logic and the repository layer will take care of managing data. See you in the next lecture. Welcome back. In this session, we will refactor the service layer to enhance the separation of concerns by introducing a new repository layer to handle our data. We will create a user repository interface under the repository package. We will implement this interface in a class called user repository impl and annotate it with the @repository to register it as a Spring Bean. Let's start by copying our existing users list to our new class. We will inject an instance of the user repository into our user service class using the constructor injection. Also, let's get rid of the users list instantiation. We will start by refactoring the getAllUsers method. Instead of handling the users list directly in the service, we will delegate this call to the repository layer using a new method called findAll and return the users list from the repository. We will refactor the getUser method by creating a new method in the repository called findById that encapsulates the logic within the repository layer. We will generate the method, implement it, then paste the code in the user repository impl class. For the createUser method, we will introduce a save method in the repository that accepts a user as a parameter. We will also refactor the user ID generation logic to reside within the repository itself. We don't have the ID to pass it to the constructor anymore. Instead, we will have a temporary setID method which will be removed later. Let's generate and implement the method. In the repository, we will use Java streams to map the user IDs, find the max ID, and increment it by 1. We need to set the newly generated user ID and add the user to the list. The updateUser method will reuse the findById to fetch the user and update its values. So, minimal changes are needed here. Lastly, for the deleteUser method, let's create a new method called deleteById in the repository to encapsulate the logic of deleting a user. Let's create the method, implement it, and simply paste our previous code. By doing these changes, we already enhanced the separation of concerns by delegating the data management to our repository. We will clean the code by removing the calls to the invalid constructors. Back in the user service, we will remove the unused users list, making our service layer more focused. To test our changes, let's start by running the server and open Postman. We will start by calling the getUsers method, and as expected, we got an empty list. Next, let's use the postUser API to create two users with unique emails. Let's update the first name of the second user using the putUser API. We will use the getUsers endpoint to validate our users were created and updated successfully. Let's test the deleteUser endpoint by deleting the user with ID 1 and validate getting a response. Finally, let's confirm the getUsers API is still working by fetching the details of the user with ID 2. In this session, we successfully moved our data management logic to the repository layer, completing our three-layered architecture. However, we still lose data whenever we restart our application. In the next lecture, we will introduce a database to persist our data that can survive application's restart. See you in the next lecture. As you may already know, having a database is essential for almost any application. In this lecture, we will introduce the H2 in-memory database, but we will configure it slightly different to persist our data into a file so they can survive application restarts. This will allow us to persist our data and test GPA entities without the need to install MySQL just yet. We will start by adding two dependencies. The Spring Boot Starter Data GPA. This will manage our entities and database connection. Also, we need the H2 database plugin to provide an in-memory database that also supports file-based persistence. Once we added our dependencies, we will hit the Maven reload button to synchronize our dependencies, and we are good to go. In Spring Boot applications, we can configure our database using application properties or application.yaml. I prefer the YAML syntax, but if you prefer the .properties file, I will make sure to attach it to the resources of this lecture. For our data source, we need to specify the URL under Spring Data Source URL, and since we are using the H2 with file persistence, it should start with JDBC H2 file and the location where this file should be created. For username and password, let's use the SA for simplicity. We will provide the driver class as org.h2.driver. We need to define the database dialect so that Hibernate knows which dialect to use. For that, we will use the Spring GPA database platform and set it to org.hibernate.dialect.h2 dialect. When using H2 database, it will have a race condition with our Spring context. To fix the issue, we will delay the data source setup until Spring context initializes. We will let Hibernate automatically generate our database tables using hibernate.ddl-auto and set it to update. This will ensure creating new tables if they don't exist and updating the fields for existing ones. Lastly, to access our H2 console, we can enable it using the spring.h2.console.enabled and set it to true. This will allow us to access our H2 console and view our database and tables on localhost 8080/h2-console. Our connection configuration is done, but we are not using it yet. To allow GPA to map our entities to the database tables, we will navigate to the user class and add the @entity annotation. This will tell Spring GPA to treat the user class as database entity. Also, we will add the @table annotation with a name attribute such as t_user. Let's add @ID annotation to our ID field and set the ID generation strategy to generation type.identity. This will push the responsibility of generating new auto-incremented IDs to the database. Let's add the add column annotation above the first name and last name to explicitly map them to database column names. Since GPA and our database are handling the ID generation, we can safely remove the setID method. Also, we need to add an empty constructor because it's required by GPA. In our user repository interface, we will start by extending the GPA repository. It takes two arguments. The first argument will be user mapping to our user entity, and the second argument will be of type long, matching our ID type. This way, Spring will provide the CRUD operations and we can remove our custom ones. Also, you may get surprised that the whole user repository impl class is not needed anymore. Let's navigate to user service impl. In this class, we will have two small changes. This method is returning an optional now. We will use the or else throw to retrieve the value or throw an exception if not found. We will do the same for the update user. And let's add the repository.save to persist our updated data. Simply, we are done. Now, GPA is managing our user entity and responsible for storing the data into the underlying database. To confirm everything is working as expected, feel free to run the server and navigate to Postman. From there, you can use the post, put, get all, and delete user. They should work exactly as before, with one difference. Now, if we restart the application or the whole server, we should not lose our data. As you can see, using GPA simplified our persistence layer and also managed our database connection for us without the need to manually write CRUD operations. With the foundations we have built in this module, now you are ready to tackle more advanced topics, such as Spring transactions. See you in the next module. Hey, glad you made it here. In this module, we will start with the transactions. Transactions topic by itself is a very big topic. For that, I dedicated this whole module to cover transactions on database level, or using the Java code but without the Spring framework. This will allow us to understand how really transactions work before we move on to the next module and use it with the Spring framework. So, what is a transaction? In simple words, a database transaction is a sequence of actions or operations performed on database as a single unit of work. Either all of them are successful and written to the database, or the database state doesn't get changed. Database transactions have four main characteristics: atomicity, consistency, isolation, and durability, those also known as ACID. Atomicity enforces that all operations must be completed successfully before the transaction commit to the database. If any operation fails, the entire transaction rolls back. Consistency guarantees that the database remains in a valid state before and after a transaction. The isolation, it ensures that the immediate state of a transaction is not visible until it's committed. Lastly, durability means once a transaction is committed, these changes save to the database and can survive system failures, power outage, and even crashes. Even with these definitions, it's still a little bit abstract. So let's dive into some examples and make it more concrete. Let's assume we started a transaction that's calling an operation. It could be an insert, update, or delete operation. It doesn't matter. The operation was successful, and in this case, the transaction will be committed and the database will have a new state which reflects the new changes caused by our transaction. In the second scenario, our transaction is calling 3 operations. Let's assume all 3 operations were successful. In this case, our changes will be committed to the database. In the third scenario, we also have 3 operations, but this time the second operation failed. In this case, the third operation will never get executed. Also, the transaction will be rolled back. Rolling back the transaction means canceling operation 1 and the database will remain in the state as before the transaction started. Hopefully, this gave you an idea on what is a transaction and how it works. In the next lecture, we will get our hands dirty and start working with transactions on database level. See you in the next lecture. In this lecture, we will install Docker and MySQL. We will be using Docker to run MySQL inside a container, and later we will use it to create MySQL database on the fly for our integration tests. Also, we will use it to run our Angular application without the need to install Node.js or any other dependency. To install Docker, we will navigate to docker.com and download the Docker image that matches our operating system. Once the download is complete, we will install it by following the instructions. I have Docker already installed, but I will replace it and have the latest version. The installation should be straightforward, and once done, we can open the Docker desktop and you should have a page similar to this one. Now that we have Docker installed, it's time to set up MySQL. We have several ways to set up MySQL within Docker. In this lecture, we will cover two approaches, using the Docker desktop directly or from the command line. And in the upcoming sections, we will cover two more approaches, using the Docker Compose and also how to use annotations to run temporary MySQL for our integration tests. Let's start with the first approach and pull the MySQL image directly from Docker. From the search bar, we will search for MySQL and pull the latest image available. Once the image is pulled, we can run the container by clicking the Run button. Let's give our container a name. Let's call it MySQL-container. For the port, we will redirect from the host port 3306 to the container port 3306, which is the default port for MySQL. But be careful, if you already have MySQL installed, this port will be reserved already. For that, you can use a different port, like 3307, 3308, or any other port. Before we can run MySQL, we need to define a root password. For this approach, I will use the random password. We can achieve that using the variable MySQL_random_root_password and give it the value of true. I will hit run, and as you can see, the instantiation of MySQL already started. Here in the logs, as you can see, MySQL automatically generated a random password. We will copy this password because we need to use it very soon. If you are not already on the logs tab, we can access it from the containers and click the MySQL container, then the logs tab. MySQL is running and we acquired the auto-generated password. So let's connect to MySQL using the exec tab. We can connect to MySQL using the following command: the -u for username and -p for the password. We will hit enter and paste our password. As you can see, we were able to connect to MySQL successfully. We can list all databases using the command show databases. We can also create a new schema. Let's create a testDB schema. And we will use the show databases again to get our newly created schema. It's time to switch to our second approach of running MySQL inside Docker container. For this one, we will use the command line. Inside the command line, we will use docker run name and define our container name. Also, we need to provide an environment variable. This time, I will define the root password as root, and we'll use the -p to define our port. We will connect the host port 3307 and forward it to the container port of 3306. You may notice we are reusing the same port 3306 on the container because each container is running completely in isolation and we can use the same ports on different containers. We will add the -d to run in detached mode, and at the end, we will define our image name, MySQL:latest. After hitting enter, now we have two containers running. We can connect to our new MySQL container, same as before, using the exec tab, but we can do it differently using the command line. Let's switch back to the command line and run docker exec, which stands for execute, and we need to have an interactive terminal using the -it. We will pass our container name and bash at the end to define our terminal. We were able to successfully connect to our Docker container, and now our commands are executing inside the Docker itself. So we can use the MySQL command, but this time I will provide my predefined password root. Make sure there's no space between the -p and the password. If we run show databases, we will not get the testdb database, which we already created in the other container. So those containers are running completely in isolation. Now our environment is ready to start working with transactions. See you in the next lecture. Hey there. In this lecture, we will learn how to manage transactions using the MySQL console. In this lecture, I will need two terminals running at the same time to be able to demonstrate how transactions work. This might be a little bit confusing. I hope you will be able to follow. But if something wasn't clear or you have any questions, feel free to ask in the Q&A section. So, from Docker, I will navigate to the exec tab and connect to MySQL server using the same MySQL command as before. We will need to create a new schema that will store banks and accounts information. Maybe accounting is a good name for this schema. We need to set accounting as our current schema by using the command use accounting. Let's create banks table that has two columns. The ID column of type int, it's an auto increment, and set it as primary key. The name will be of type varchar with a maximum length of 100 characters, and it could not be null. We can quickly confirm our table was created using the command show tables. Let's insert a record into our banks table with the name JP Morgan. To view the data, we will select all records from banks, and it will return the record we just created. When dealing with single operations like inserting a single record, transactions might not seem necessary. Typically, the operation will either succeed and commit to the database or fail and roll back. However, there's an edge case where transactions are useful even with single operation. For example, when updating or deleting multiple records, you may want to validate data before committing the changes to the database. So let's explore how to control transactions in MySQL. There are two main ways. The first is by disabling the auto-commit mode. By default, MySQL runs in auto-commit mode, meaning each individual SQL statement is treated as a transaction and automatically committed as soon it executes successfully. To disable auto-commit mode, we can set it to 0. We will insert a new record with the name Deutsche Bank. To demonstrate how transactions work, we need a second session. We can achieve that by using a second terminal. In another terminal, we will connect to Docker and log into the same database using the same command, MySQL-u root-p, and enter the password. Once connected, we will set the current schema to accounting. In the new terminal, if we select all records from the banks table, the second record will not appear because it hasn't been committed yet. This shows that transactions run in isolation. Of course, we can modify isolation level and view uncommitted changes, but we will cover that in later sections. If we switch back to our first terminal and commit our transaction, we should be able to see the Deutsche Bank record in the second terminal. We know how to disable auto-commit mode and manually commit our transactions. But what happens if we roll back a transaction instead of committing it? We will insert another record to the bank's table. This time, we will choose the name Revolut. Instead of committing the transaction, I will roll it back using the rollback command. Switching to the second terminal and fetching all records, notice that the record Revolut doesn't appear. This is because the transaction was rolled back, so changes were not saved to the database. Now it's time to cover the second approach of managing transactions. This approach is widely used in production environments because it provides a greater control on how and when changes are applied to database. We will enable the auto-commit mode by setting it to 1. Then start a transaction by executing the command start transaction. I will execute the same insert statement with the name Revolut and then commit the transaction. Switching to the second terminal, we can see the record for Revolut. If we had checked before committing the transaction, the record would not have appeared just like in the previous example. Notice something interesting. The ID for Revolut is 4 and the ID 3 is missing. This happened because the previous transaction was rolled back. When a transaction is rolled back, any auto-incremented IDs used in that transaction are not reused. Before moving on, I will demonstrate a scenario where using transactions might not be necessary. Let's say we are inserting a list of banks, Bank 1, Bank 2, and Bank 3. These records are independent of each other, meaning they don't rely on any shared state. In such cases, there's no need to use transactions. Inserting them individually without wrapping them with transaction will be faster. Using a transaction here would only slow down the process. This highlights an important point. Be mindful when using transactions and only apply them when required. Since we don't need the records we just inserted, I will roll back the transaction and discard them. And we can prove that the records are not in the database. So, when transactions are necessary, to illustrate that, we will create accounts table and allow customers to transfer money between accounts. We will start by creating a new table called accounts with 4 columns: ID, bank ID, number, and account. The ID column is an auto-incremented primary key. The bank ID column of type int and not null. The number column is varchar with a maximum length of 20 characters, and the balance of type decimal, which also cannot be null. We also need to add a foreign key constraint to the bank ID column, having a reference on the ID column from the banks table. Running the show tables, we have 2 tables, banks and accounts. First, we will insert a record with the bank ID of 1, account number of customer 001, and a balance of €1,000. Next, we will insert another record with the account number of customer 002 and bank ID of 4. We can view the records in the account table by running the command select all from accounts. Let's say we need to transfer €100 from customer 1 to customer 2. We can do this by updating the balance of both accounts. We will start by updating the balance for customer 1 by subtracting €100. Then we will update the balance of customer 2 by adding the €100. If we run the command select all from accounts, we can see the updated balances. We just received a new task to transfer €500 from the account of customer 2 to customer 1. We will execute the same logic as before, decreasing customer 2 balance by 500 euros and move it to customer 1 balance. We have an exception that the total balance of any account cannot exceed 1,100 euros. I manually added a trigger to the accounts table to demonstrate MySQL throwing an exception using the code below. The problem now, if we fetch the data from the accounts table, we deducted 500 euros from customer 2 but never sent them to customer 1. This is where transactions come in handy. We will repeat the same scenario, but this time we will wrap the two update statements within the same transaction. We will deduct 500 euros from customer 2. While adding 500 euros to customer 1, same exception will be thrown. But we can roll back the transaction and the changes will be discarded. If we check the account balances again, we can see that the balances are the same as before the transaction started. Hopefully, this gave you a basic understanding on how transactions work within MySQL. This is just a foundation, and there's much more to explore. In the next lecture, we will cover transaction save points and see how can they be used to roll back to a specific point within a transaction. See you in the next lecture. Hey, today we will cover the save point, which acts as a checkpoint within the transaction. It allows us to roll back to a specific point within the transaction without the need to roll back the whole transaction. This feature may come in handy when dealing with complex operations. To better understand save points and how to use them, let's consider this example. Imagine Adam needs to do a bank transfer. He opens his banking app and wants to transfer 500 euros from his account to his mother's account. First, he selected the main account as source account. He filled out her name and account number, and even chose to save her details as a contact for future transfers. After entering the amount, he hit send to complete the transaction. Here's what's gonna happen in the background. The application will open a new transaction, and within that transaction, it will save the contact details, deduct 500 euros from his account, and credit that 500 euros to the destination account. But this time, we will create a save point called contact created. In this scenario, if the contact creation was successful and we managed to deduct from his account, but while crediting the other account, an exception happened, we can now roll back to our save point without losing the operation of saving the contact. This approach keeps the database consistent, preventing incomplete transactions and enhance the user experience. Now that we have an overview how save points work, let's implement it using MySQL. I will start by running Docker and log in to our previous database using the same credentials from before. We need to create a table with the following structure: an ID column, which is an auto-incremented primary key, account ID of type int and not null, a name column of type varchar with maximum length of 50 characters, and lastly, an account number with the varchar of maximum 20 characters. We will use this table to link each account with its contacts by providing the contact name and contact account number. Now, we will use the accounts table from the previous lecture to insert a couple of records for each of Adam's and his mother's accounts. We can insert into accounts ID, bank ID, number, and balance the values 1 to 3 representing the account ID, 1 for the bank ID. Let's have zeros as the account number and a balance of 1,500 euros. For his mother's account, we will use 456 as the account ID, 2 as our bank ID, and the following account number and a balance of 800 euros. We can now simulate doing the transfer. This process, as explained before, it will include starting a transaction, creating the contact details, deducting 500 euros from the source account, and credit 500 euros to the destination account. So let's implement that by starting a transaction using the start transaction. We will insert into contacts account ID, name, and account number the values of 123, Fatima as the name, and the same account number as before. We will create a save point using save point and give it a name of contact created. This could be any name you prefer. After that, we will deduct 500 euros from Adam's account by using the update accounts and set the balance to the current balance minus 500 euros, where the ID equal 123. Next, we will update his mom's account by adding 500 euros, where the account ID equal 456. As we can see, we are facing the same issue as before. The account balance could not exceed 1,100 euros. So, we need to roll back, but this time we have the option to roll back to our save point using the rollback to save point and give it the save point name. After that, it's necessary to commit. Rolling back to a save point alone would not commit the transaction. To verify our theory, let's select the contacts. As we can see, the contacts details were persisted successfully. But when selecting the accounts, there were no changes made to this table, and the balances remain as before the transaction started. This gave us more control over the transaction, and we could have several save points within a single transaction. Even it's not the most used way to control a transaction, it's still very important to know that save points exist and how to use them. In the next lecture, we will implement a similar example but using plain Java. It will be our entry point to start using transactions within Java projects. See you in the next lecture. Hello there. In this lecture, we will implement the same example from previous lecture, but this time we will be using plain Java instead of the MySQL console. So let's dive right in and open our IDE. A quick note, I will be using IntelliJ, the ultimate version for the entire course. So if you are on the community version or using a different IDE, things may look a little bit different for you, but don't worry, you will still be able to follow along. Let's start by creating a new Java project and call it bank transfers. We will leave everything as it is with default values. For this project, we will need a single Maven dependency. MySQL connector Java from the MySQL group ID will allow us to connect to the MySQL. After adding the dependency, hit the Maven reload button to refresh the dependencies, or from the terminal, you can run the command maven clean install. Once the dependencies are downloaded, we are ready to move on. Our whole application will consist of a single class. So under the source main Java, let's create a new class and call it bank transfer. We need to add the public static main void to make our class executable. Before we proceed with the implementation, I will connect to MySQL directly from the IDE to avoid switching to the terminal. If your IDE doesn't support this feature, don't worry. You can still follow along by connecting to MySQL from the terminal or using any tool like MySQL Workbench. From the Database tab in IntelliJ, I will create a new data source using the MySQL driver. We will connect to the database on our local host using the root as username and password. I will also use the accounting database which we created earlier. After successfully connecting, we will copy the JDBC URL which we will use shortly and hit OK. As a quick reminder, in total we have 3 tables. The accounts table have 4 records in total and the contacts table has a single record. Now, back to our bank transfer class, let's set up our database credentials by storing them in constant variables. We will start with a private static final string for the URL, and we will paste the JDBC URL we just copied. We will do the same for the username and assign it the value of root. For the password, we will duplicate this code and change the variable name to password. Our code will be responsible to do the same exact thing as before. It will open a connection to our database, insert the new contact, deduct from the first account, and credit that amount to the other account. Let's start by opening a new connection to our database using the try with resources statement, which will handle closing our connection automatically for us, which is equal to the driver manager.getConnection from the URL, username, and password. We need to make sure it doesn't auto-commit using the connection.setAutoCommit to false. To insert a new contact, we will use a string variable to create our contact SQL with a value insert into contacts the account ID, name, account number, the values of 3 question marks, which act as a parameter placeholder for our prepared statement. Then we will also use the try with resources statement to wrap our prepared statement, which equals to connection.prepareStatement, and pass in our create contact SQL string. Now we need to assign variables for our parameter placeholders, and we can do that by assigning the type and the index. So for the first parameter of index 1, it's of type long and have the value 1 to 3. For the second parameter, it's of type string and we assign it the value Fatima. For the third value, it's of type string and we assign it the account number. After that, we can execute our query by using statement.executeUpdate. Same as we did with the MySQL, we could have also save points. For our save point, we will call it contact_created_SavePoint and assign it the value of connection.setSavePoint with the variable contact_created. So we still have two actions, debiting the first account and crediting the second account. For deducting from the account, we will create a variable debtAccountSQL with the value updateAccounts, which sets the balance to the current balance minus 500, where ID equal to parameter placeholder. Same as before, within a try with resources statement, we will have a prepared statement called debtStatement with a value of connection.prepareStatement and pass in our debtAccountSQL query. We have one parameter to set, which is of type long and has a value of 1 to 3. Then we can execute our update query. In case, while deducting from the account or crediting the other account, an exception occurred, we will roll back to our save point, commit the transaction because it's necessary, then we will restore the exception. For the credit account, we will do exactly the same as before with a credit account SQL which updates the account and sets the balance to the current balance, but this time we will add the 500, where the ID equal to our parameter placeholder. Then, within the prepared statement, we will pass in the credit account SQL. We will assign our ID to value 456. Finally, we can commit our transaction using the connection.commit. Now the implementation is done. We can run it by running the main method and test if everything is working as expected. In our case, it will throw an exception and the account's balance should remain unchanged, while the new contact should be recorded successfully to our database. This lecture demonstrated how to use plain Java to connect to our MySQL database and manage transactions. But it's not the most convenient way to manage transactions. In the next module, we will start our journey how to manage MySQL transactions using Spring Framework. See you in the next module. Hello there. Spring Transaction is a powerful mechanism. It manages database transactions efficiently and ensures data consistency. It acts as a high-level abstraction over our traditional transaction management, simplifying database interaction while handling connection setup and managing resources. Before you proceed with this module, if you find yourself in any of these situations, struggling to set up a Spring Boot application, encountering unfamiliar terms, or you are new to the Spring framework and skipped the Introduction to Spring lectures, I recommend you to go back and revisit the Introduction to Spring Framework sections. This will help you build the solid foundation needed before diving into more advanced topics. And of course, at any point of time, if something isn't clear, I encourage you to use the Q&A section and I will get back to you as soon as possible. Now, let's get started. Hello. To test our backend throughout this course, we will be using two approaches, our bit and byte Angular application and Postman. So let's start by setting up our Angular application. To make setting up the Angular project convenient, I have created a Docker image which contains the project and all the dependencies needed. This way, running the Docker image will provide us with a running Angular application which we can use to test our backend. To download our Docker image, we will run Docker and search for Hussein Akar /bit and byte app. Or from the terminal, we can execute the command docker pull Hussein Akar /bit and byte app latest. To run our Angular project, we simply hit the run button, then provide a name for our container. We will also bind our server port 4200 to our container port 4200. With the following minimal configuration, we can now run our container. Assuming you already have Postman installed from previous lectures, we will open Postman and import a new collection. The collection is available for download under the resources of this lecture, with the name springtransactions.postmancollection.json. We need to unzip the file and import it to our Postman. This will load all the backend APIs under the Spring Transactions collection. Finally, we will create a new Spring Boot project by firing our browser and navigate to Spring Initializer website as we practiced in our Introduction to Spring Framework module. We will call our project bit and byte and leave everything else as it is. For the dependencies, make sure to include Spring Web, Spring Data GPA, and MySQL connector for Java. We can now hit the Generate button to download our project. We need to unzip it and import it to our IDE. I will use the application YAML to configure our application, but feel free to use the application.properties if you prefer that. Mainly, for now, we will configure the connection to database. Under spring.datasource.url, we will connect to jdbc:/mysql:2/ localhost 3306, which is the default port for MySQL /bit and byte. Then we can add a question mark with create database if not exist and give it the value of true. This will ensure our database will get automatically created if it doesn't exist. And as you expect, this variable should be only used on your local environment. Never push that to production. We will have a username of root and password of root. Also, we will define the driver class name as com.mysql.cj.jdbc.driver. Under spring.gpa.hibernate section, we will define the variable ddl-auto and give it the value update. This will automatically update our database schema to match our entities, which also shouldn't be in production, where Flyway would be a much better fit for that case. For the naming of our auto-generated MySQL tables, we define the physical strategy as org.hibernate.boot.model.naming and give it the value physical naming strategy standard implementation, which will prevent automatically applying naming conventions like camel case or snake case. Now, we will run the server, and from the browser, I will open a new tab. We can access our server on localhost 8080. Getting a white label error page means our server is running. Also, we could verify that Hibernate was able to automatically generate our database by navigating to Docker, and from within the MySQL container, we can run mysql-u root-p, and we enter the password. Running the command show databases, we can see that our database was automatically generated through our Java application. Our project setup is ready. We have a Spring Boot application running our backend, an Angular app running as our front end, a Postman with collections to help us test edge cases, and our database automatically generated by our Java application. In the next lecture, we will start exploring Spring transactions within the Spring framework. See you there. Hello. In this lecture, we will start building our backend for our front-end application. So from our bit and byte app, which we can access on localhost 4200, we have the categories tab, which will be our starting point. Back to our IDE, we will start by creating a new class called category under the product.domain. We need to annotate our class with the @entity and @table annotations. Spring entities need an ID. Also, from the UI, we know for the category we need a single field, which is the string name. We will annotate our ID field with the @ID annotation, also the generated value with the strategy of generated type.identity. The identity strategy will delegate generating auto-incremented IDs to our database. For the name field, we could add @column annotation with length of 50 and nullable equal false. As usual, GPA entities require an empty constructor. We will also define a constructor with the name field. Then we will generate a getter for both the ID and the name. We could also have our empty constructor access level as protected. With that, our entity is mapped to GPA and ready to be used. Let's create our controller, the entry point for our categories, by creating a new package called controller and create category controller class. We will annotate our controller with the REST controller annotation. Also, add request mapping annotation with /categories. Our first function will return a response entity of list of category. We will fetch the list of category called categories from the category service.getCategories. Then we will return those categories. We need to annotate our method with the getMapping annotation. Also, since Spring Boot version 3 and above, wrapping our response inside a response entity is not required anymore, so we can remove it and have a cleaner code. We need to generate our category service. Also, we will include it in our constructor to benefit from dependency injection, and better to have it as final. Now, we can generate an interface under the service package. Then, implement our interface under service.impl. Let's annotate our service with the @service annotation. And back to our controller, we will auto-generate the method getCategories and implement that method in the category service impl class. This method should return categories from database. So, to fetch data from database, we need a category repository interface with GPA repository with parameters category and long. We will have access to our category repository by injecting it using constructor injection. Now, we can simply return category repository.findAll. Since we don't have any categories in our database, we will connect to the database and generate at least one category to test. I will connect to a new data source on my local host with the root for both username and password, and the bit and byte as our database. We will run our server once to generate the category table. After that, we can access the table and manually add pizza as our first category. Navigating to our Angular application and refreshing the page, we still receive an exception. But if we look into our network tab, we have a course error. This happens because Angular initiating a pre-flight request. So, if we trigger the same call from a new tab outside the Angular, it should receive our category without any issues. To fix the issue, we will create a course configuration class. So from our IDE, under the core.config package, we will create course configuration Java class. Our class is annotated with the add configuration annotation so that it gets registered in the Spring context and run before other classes. This class will implement the WebMVC configurer and override the add course mapping function. To allow the calls from our Angular app inside the registry, we will add the mapping for /2stars. Also, we will allow the origins from the HTTP localhost 4200, which is our local Angular application URL. Also, we allow the methods get, post, put, delete, and options. And for the headers, we will allow all the headers. If we restart the server and back to our browser, we can refresh our Angular application page and we should successfully fetch the data. In this lecture, we covered one of the most confusing exceptions once you start calling your backend APIs from Angular application. See you in the next lecture. Hello. From this session onward, things will get more interesting. We will start with one of the most misused features whenever working with transactions. We will explore the issue by debugging our application, then we will find the proper solution. So, from our IDE, we will place a breakpoint inside the category controller class. If we run the server in a debug mode and call the categories endpoint, we will notice that there's no transaction-related logs are showing up. So, to enable logging, we will navigate to application YAML and add under logging.level.root and assign it the value of info. For the org.springframework.orm, we will have the log level of trace. Same for org.springframework.transaction. And for org.hibernate.engine.transaction.internal transaction implementation, we will assign it the value of trace. This configuration will give more than enough information to debug our transaction. Restarting the server and refreshing the browser, our request will reach the breakpoint. Switching to the console tab, we can see the logs related to transactions. One key log entry is opening GPA Entity Manager in Open Entity Manager in View Interceptor. This confirms that transaction-related info are being logged. If we release the breakpoint, we also see a thread-bounded Entity Manager with a session ID, which tells us that a session is already opened. Don't worry about the meaning of those logs for now. We will cover them in details later. To better understand what is happening, let's create a class that logs the database connections so we can monitor how many open connections we have. We will add our class under the core package and call it database connection logger. We will annotate our class with the add component annotation so it gets registered as a Spring Bean. Next, we will generate a constructor and inject the session factory. Since we don't want the logger to block our main application execution, we will execute the logging logic inside a new thread, and we should start that thread. Inside the new thread, we will introduce a short delay between the logs by calling thread.sleep with a duration of 2 seconds. It should be placed inside a try-catch block to handle the potential interrupted exception. Finally, we will print the number of opened connections by calling system.out.println and pass in the session factory.getStatistics.getSessionOpenCount. We will also duplicate the code, but this time we will print the number of closed connections. Since the Hibernate statistics is disabled by default because it has an impact on performance, we need to enable it from the application YAML. Under spring.gpa.properties, we could add hibernate.generateStatistics and set it to true. Restarting the server and calling our categories endpoint, in the console, we can see the number of opened and closed connections. If they match, there is nothing to worry about. However, if we refresh the browser, we notice something interesting. The number of opened connections is 5, but the number of closed connections is 4. That means we still have one opened connection, and it's not being released until the function inside the controller finish executing. To make the issue more visible without using breakpoints, let's simulate a call to an external microservice that takes some time to respond. We will do that by calling a method this.slowRemoteCall and pass in the categories. We will let the IDE generate the method. Then we will simulate calling the external microservice by reusing the thread.sleep. This time, we will let our method sleep for 5 seconds. And of course, we will wrap it with try-catch block. Now, after restarting the server and refreshing the page, we observe the number of opened connections is 4 and number of closed connections is 3. This means a single user is already causing a connection build up. What would happen if we have 300 active users? A huge number of open connections will pile up, eventually leading to a crash. To prove our theory, we will do a simple load test. I already included a script inside the bit and byte Docker image that will call our categories endpoint 300 times in parallel. To execute our load test from Docker Desktop, we will navigate to our bit and byte app container, then to the exec tab. We need to change the directory to user local bin, and let's check the available files using the ls command. We have our curl script bash file in place. So, after running the backend in non-debugging mode, we will execute the script using sh and pass in the file name. At first, everything works fine, and we are getting responses from our backend. But 30 seconds later, we start getting internal server errors. Checking the IDE console, we find the following exception. Connection is not available and request timed out after 30 seconds. The root cause of this issue is the open session in view, where our API call being intercepted by open-in-view interceptor and it opens a transaction. But that transaction will be held opened until we return a response. Our load test clearly shows that open-in-view is keeping the connection open for too long, eventually exhausting our available connections. The good news is the fix is straightforward. In the application YAML, under spring.gpa, we will add open-in-view and set the value to false. Restart the server and run the script again. This time, everything works perfectly and without any issues. As we have seen, Spring comes by default with open-in-view enabled, which cause open connections to pile up. Also, it could cause system failure. However, disabling it in a running production can cause different type of issues, so please don't disable it yet. Follow along with this course, and at the end, you will have a full understanding how to manage transactions without relying on the open-in-view interceptor. Until then, we will keep our production environment as it is. See you in the next lecture. Hello there. Transactional annotation allow us to dynamically execute a method within a transaction without the need to explicitly open or close the connection or manually commit or roll back the transaction. It could be applied on both class or method level. When applied on a class level, it gets automatically applied on all the methods within that class unless that method is also annotated with its own transactional configuration. To start using the transactional annotation, we will implement the add category feature while using the transactional annotation to manage our transaction. From the IDE, we will comment out the slow remote call method so it doesn't slow down our application during testing. Then we will create a new method named createCategory, which returns a response entity of type category. Since our API is responsible for creating a new category, it will be annotated with the post mapping annotation. Our method requires a request body. So let's create a new class called category payload under the payload package. You could also name this class createCategoryRequest, createCategoryCommand, or anything meaningful. A good fit for our use case would be converting this class to a record with a single field of type string. We will not be covering input validation within this course, but this is the right place to implement Spring validation or your custom validation if needed. Let's go back to our controller and add @requestBody category payload as a method parameter. Let's call the variable payload. We assume createCategory will return a long representing the ID of the newly created category. So we will assign this value from the category service.createCategory and pass in our payload, and return a response using responseEntity.created with URI.create from our categories and pass in our newly created ID, then we call build. Now we should define our createCategory method in the category service and implement that method in the category service impl class. Inside the implementation, we will create a new category object, set its name from the payload value, then save it using the category repository.save and pass in the category. Finally, we will return the ID of the newly created category. Let's now start the server, set a few breakpoints, and go to our Angular application. Try creating a new category called drinks and click the Add button. When the request hits our first breakpoint, check out the logs. At this stage, there is no transaction-related entries in our logs. If we clear our console and continue to the next breakpoint inside the category service, we will notice that the number of opened and closed connections remains the same. This indicates that no transaction has been started yet. The logs also clearly state there is no need to create a transaction. Once the save method is executed, several logs appear indicating a new transaction was created. A session is opened, bounded to database connection, and closed immediately after the transaction is committed. Back in our browser, you will see the drinks category was successfully added. Let's analyze the transactional behavior by adding another category called side dishes and repeat the same debugging process. You will notice that the side dishes is added to the database before the createCategory method completes execution. A transaction is created specifically for the save operation, which is then committed before moving to the next line of code. This behavior highlights a potential risk. If multiple database operations were involved, each would execute in its own isolated transaction. That's why wrapping a single operation inside a transaction is considered a good practice. It ensures consistency, especially when our application grows. We could not guarantee that there's no more operations will be added to our method. To ensure our entire logic executes within a single, cohesive transaction, we should wrap it using the transaction annotation on the service layer. But before doing that, let's look what would happen if the transaction annotation was misused. For instance, let's place it on the controller class. Doing this reintroduced the same problem we solved when we disabled the OpenIn view. It will hold a database connection opened for the entire duration of the HTTP request. This approach is inefficient, risks overusing resources, and undermines proper transaction boundaries. To verify this, let's restart the server and create a new category called main. You will notice that our session is opened even before the controller method executes. Our main category is not visible in the database until after the controller method finishes executing. This approach introduces one more problem. Let's assume an exception occurred on the controller level. Since our transaction wasn't committed yet to our database, it will be rolled back and never get persisted. Even our service layer was done executing. We will explore this problem in later lectures. So, let's simulate a call for an external service, same as we did before using the slow remote call. We would still face the issue of too many open connections. This is why it's not recommended to have our transactional annotation on controller level, irrespective if it's placed on a class or method level. Transaction management should always belong to the service layer, where business logic resides. Let's do it the right way and apply our transactional annotation above the service layer method. Restart the server, add a new category, and debug the application. This time, you will notice that the pasta is added to the database only after the create category method complete execution, but before the slow remote call begins. That's exactly the behavior we want. As a conclusion, we should always place our transactional annotation over the service layer. And of course, now you have many questions regarding when, where, and how to use transactional annotation properly. In the upcoming lectures, we will answer most, if not all, your questions. See you in the next lecture. Hello. In this lecture, we will implement the update category functionality to demonstrate how transactional update works in practice. This gives us a hands-on experience on how consistency and integrity are maintained during data modification. From our IDE, under the category controller class, we will start by implementing a new method that returns a category called update category. This method requires a request body, so we will reuse the category payload class we created earlier. We also need to annotate our method with the put mapping annotation, including an ID as path variable. To access the ID, we will add a method parameter with the path variable annotation with type long and name ID. Since we expect a category as a response, we will call category service.update category, passing in the ID and the payload, and return the update category directly. Let's define the update category method inside the category service interface, changing the parameter name to category ID, and then implement this method inside the category service impl class. To update an existing category, we will first fetch it using the category repository.findById and pass in category ID. If the category is not found, we will throw a new entity not found exception with the message category with the ID, category ID not found. Once we have the category, we can update the name using the value from the payload. Since we don't have a setName method, we will generate it inside the category class and assign this .name to the name. Then we will save using category repository.save, passing in the category, and return it as the result. As we discussed earlier, any changes to a database should be wrapped inside a transaction. So we will annotate the update category method with the transactional annotation. We can now test our update functionality by starting the server and navigate to our Angular application. Update the main category to main courses and click the Save button. The category should be updated successfully. Back in our IDE, let's simulate a scenario where we decided not to save the update unless the name is set to pizza. This example to simulate you are calling .save only in specific cases. Restart the server and add a breakpoint to observe what happens when updating side dishes to side dish. At the breakpoint, we will notice that category repository.save was never executed. Yet, when we check the browser, the category still appears to be updated. To better understand what happened, we will check the logs. The transaction was committed even though we didn't explicitly call repository.save. To confirm this behavior, try updating side dish back to side dishes. Click the Save button and you will see the update succeeded once more. This is due to Hibernate dirty checking mechanism. Once an entity is loaded to the persistence context, Hibernate will watch the changes to that entity. At the end of the transaction, Hibernate will write those changes to the database without explicitly calling .save. While this behavior is so powerful, it comes with responsibility. You should be careful when updating an entity within transactional context, because those changes may end up in the database without explicitly calling .save. Hopefully, this walkthrough clarifies how transactional update works within Spring Boot application and help you avoid unexpected issues when updating entities within transactional context. See you in the next lecture. Hello. In the previous lecture, we explored how Hibernate dirty checking mechanism works and how it automatically tracks all the changes made to entities loaded to the persistence context. This isn't free. It introduces overhead that can impact application performance and add complexity to transaction management. So, what if we are loading an entity with no intention of modifying it? This is where read-only transactions come into the play. Let's dive into how to mark a transaction as read-only, the performance benefits it offers, and the pitfalls developers should watch for. From our controller, we will add delete mapping annotation with the ID as path variable and declare our method with the public response entity of type void, delete category with the path variable of type long and an ID. Then we will call category service.delete category and pass in the ID. Finally, we will return response entity.noContent and call build. We will define the delete category method in the category service interface and rename the parameter to category ID. Then implement the method inside category service impl class. Let's start by marking the method with the transactional annotation. Then we will delete the category by calling category repository.delete, passing in the category. Let's run the server and test the functionality in the browser. Deleting categories like pasta, main courses, and side dishes should work as expected. Back in our IDE, you might notice connection logs still showing the count of opened and closed connections. To clean things up, open the database connection logger class and simply comment out the component annotation. This will stop it from being registered as a Spring Bean, and connection logs will disappear so we can focus on what we are debugging now. To illustrate the pitfalls of misusing read-only transaction, go back to delete category method and modify the transactional annotation by adding the read-only attribute and set it to true. Restart the server and try deleting drinks category. You will notice that the delete operation is no longer working. The same would happen if we navigate to the update category method and also add the read-only attribute. Even if we explicitly call repository.save or repository.delete, it would not persist the changes. That's because the transaction is explicitly marked as read-only. Spring will suppress any data modifications within it. In this lecture, we looked into how marking a transaction as read-only is considered a good practice because it eliminates the unnecessary change tracking and it improves performance. But we also saw the downside when it's misused and placed on a method which is modifying data. In those cases, the update and delete operations will not be persisted to our database and they will lead to unexpected results. Hello there. As we saw in the previous two lectures, simply adding the transactional annotation above a method is more than enough to execute that method within transactional context. But how Spring does that behind the scene? Let's take a closer look on how Spring uses proxies to manage transactions. We will reuse the update category method from earlier, which resides in the category service impl class. Once we have annotated the method with transactional annotation, Spring Magic takes over. It creates a proxy around the category service impl class and intercepts the method calls. The proxy, known as transactional proxy, is responsible for handling the transaction, starting, committing, and rolling back if needed. So, when we call the update category method, Spring intercepts the call, starts a transaction, and then delegates the actual method execution to the real method. Once the method completes, Spring either commit or roll back the transaction if an exception occurred. The beauty of this approach is that the other components in the application don't need to know anything about transaction management or that the proxy even exists. They can simply call the method, and Spring takes care of everything related to transaction management. This is the power of Spring's declarative transaction management. I hope this lecture clarifies how Spring manages transactions behind the scene. See you in the next lecture. Hello there. Since we completed the add, update, and delete category, it's time to move on to the product tab. From our IDE, we will start by creating the product entity under the product domain package. As always, we will annotate our class with the entity and table annotations and call the table product. For our fields, we will need an ID of type long and annotated with the @ID annotation, and a generated value with strategy of generated type.identity. A category field of type category annotated with the @many-to-one annotation, since multiple products can belong to the same category. Also, a join column with the name category_ID to define our database column name. We also need a private string name, a private string image URL, private big decimal price, and private string size. We will also annotate the image URL field with the @column annotation with the name image_URL. We could also add the @column annotation to other fields as well. I will do it for the name field only with the @column annotation with length of 50 and nullable false. As always, we need an empty constructor. We also add another constructor with all fields except the ID, followed by the getters for all the fields. We will create the product repository interface under product.repository package. Our product repository will extend the GPA repository with the class product and ID type long. Let's create our controller. Under the product.controller package, we will add a product controller class, annotating our controller with the @REST-controller annotation and @request mapping/products. This time, we will start by creating our service using private final product service and create it inside the product service package. We will implement our service interface under the impl package and annotate it with the @service annotation. Let's inject our product repository using constructor injection. Back to our controller, we will inject product service via constructor injection and declare a method to fetch all products. Our method implementation will be a public method which returns a list of products and call it getProducts. Because our method is responsible to return data, we will annotate it with the getMapping annotation. Inside the implementation, we will create a list of products and fetch them from the product service.getProducts. Finally, we will return our products. After generating the method in the service layer, we will implement getProducts by calling product_repository.findAll. Our implementation is ready. Let's run the application and test the endpoint. Since our database is empty, we will insert a sample product with the category ID 1, veggies as a name, 6 as the price, with size small, and paste in the image URL. Let's place some breakpoints, refresh our Angular application, and inspect the behavior. At first glance, the console is cluttered with statistics, making it hard to read the logs. To clean things up, we will update the application YAML by adding under Spring GPA properties Hibernate show SQL and set it to true, and disable the statistics by setting the generate statistics to false. After restarting the server and refreshing the page, we will see SQL queries in the console. But we have multiple sessions due to Angular making separated calls to fetch categories and products. To simplify debugging, we will use Postman instead to send a single request and make our debugging process easier. From Postman, we already have the setup ready, so we will execute the get products request. It will land in our breakpoint in the product controller. Let's clear the console and proceed to the next breakpoint under the product service impl class. When findAll runs, the usual stuff is happening, opening a session and creating a transaction. But we notice two queries after the findAll, one fetching the products and another is fetching category. This is known as the N+1 issue, caused by eager fetching. You might wonder, we never explicitly used eager fetch anywhere in our code. However, by default, Hibernate fetches many-to-one relationships eagerly. To validate that, we can navigate to the product class and add to the many-to-one annotation the attribute fetch equal fetchType.eager. Checking the documentation, it clearly says by default it's an eager fetch. So feel free to test the application again after adding the fetchType.eager. You should get the same result as before. In this lecture, we have seen how eager fetch can lead to performance issues due to the N+1 problem. This example had a single many-to-one annotation. Imagine what would happen if we had multiple many-to-one relationships and how many unnecessary queries would be executed. In the next lecture, we will learn how to avoid the N+1 issue, but disabling the eager fetch may introduce another type of issues. See you in the next lecture. In the previous lecture, we looked into how eager fetching can introduce performance issues, specifically the N+1 problem. Now, we will flip these scenarios. We will disable the eager fetch and explore the issues that comes up, especially related to transaction management. And of course, we will walk through how to fix them properly. Let's head up to our IDE and change the fetch type from eager to lazy. This will prevent unnecessary queries when fetching products, since we are not actually using any fields from the category entity. Let's start the server in debug mode, then use Postman to send the get products request. We will hit the breakpoint in the product controller, clear the console, and continue to the product service. Now, you will notice that the findAll executes a single query to fetch products. That's our first success. Lazy loading is helping us avoid the N+1 problem. Once we release the breakpoint, we hit an exception in the console. Could not initialize proxy, no session. To better understand what is happening, let's loop over the products and log each product category name. Restart the server and from Postman send the request again. The exception now occurs when we try to access product.getCategory.getName. Since we enabled lazy loading for our category, Hibernate didn't fetch the category while loading the product. And when we access the category, the transaction is already closed. That's what causes the lazy initialization exception. As a quick test, add the transactional annotation on the controller method. Restart the server and send the request again. Now, the category name prints just fine to the console with no error. This fix is temporary. As soon as Spring tries to serialize the response to JSON, we hit a different error. No serializer found for class Hibernate Lazy Initializer. Here what's happening. Even though the transaction is open while accessing the lazy loaded property, the serialization happens after the controller method finishes. At that point, the session is closed, so we can't access anything lazily. The JSON serializer could not process the proxy object. So, while transactional annotation on controller looks like a fix, it's really a poor workaround. Many companies switched to the open-in-view approach to fix this issue. But to fix this issue properly, we will introduce a data transfer object that will represent the data we actually want to return in our API response. Inside the product response package, we create a new record called product response. Our record will have a long ID, long category ID, a string name, string image URL, big decimal price, and string size. Our response includes all the fields needed by our front end, without exposing internal entities or triggering lazy loading during serialization. Back in a product controller, instead of returning list of product, we will return a mapped list of product response. We could also remove the for loop that logs category names. Make the same adjustment in the product service and product service impl class, and replacing the find all with a new method getProducts. Let's define that method in the product repository using a custom addQuery annotation. Select from product, new, and get the package path, and from the alias p select ID, category ID, name, image URL, price, and size. Restart the server and send the request once more. You will see that everything works fine. Products are fetched cleanly, no N+1 issues, no session errors, and no serialization failures. If you later wanted to include category name as well, just update the product response to add the string category name and modify the query to include p.category.name. In this lecture, we tackled two of the most known errors when working with transactions. So, it's always recommended to use data transfer objects to separate our persistence model from API responses. In the next lecture, we will implement the create and delete product endpoints. Try implementing them yourself before the next lecture. Hopefully, you managed to implement the create and delete product endpoints by yourself. As you may already noticed, the implementation is so similar to what we did with the category entity, except that the product depends on another entity, which is the category. So let's jump right in and start the implementation. From our IDE, let's introduce a product payload record to represent the request body when adding a product. Our payload will include a category ID, a string name, a string image URL, big decimal price, and string size. In product controller class, we will add a create product method. It will return a response entity of type void, and it will take in at request body product payload payload. Since this method is responsible to create products, we should annotate it with the post mapping annotation. For the implementation, we will declare a long product ID and set it to equal product service.createProduct and pass in the payload. It will return a response entity.created of the URI.create products and pass in our product ID, then call build. We will generate the create product method inside the product service interface. Then we will implement it inside the product service impl class. Since this method modifies data, we will annotate it with the transactional annotation. To be able to create the product, we need first to fetch the category. We will get the category by accessing the category service through constructor injection. Then we will fetch it using category service.getCategory and pass in the category ID. Now let's implement the getCategory method inside the category service. It will simply act as a delegator. It will pass our request to category repository.findById and pass in the category ID. If the category is not found, it will throw a new entity not found exception. Back to our product service, we can now create a product by passing in the payload parameters, then save it using the product repository.save. And finally, we will return the product.getID. Let's start the server and navigate to our Angular application. In the Add Product form, we will fill the name with pepperoni slice, image URL, and you can use what we have in the assets or grab URL from the browser. For the price, we will set it to equal 2.5 and the size slice. Click the Add button and we should see the new product added to the list. Let's add another product as a preparation for delete product feature. I will pick Yummy Margarita as a name, set the image URL with price 6 and size medium. Now let's implement the delete feature. We will add a delete product method which returns a response entity of type void and take in path variable of type long and call it product ID. We will annotate our method with the delete mapping annotation. For the implementation, we will simply call product service.deleteProduct, passing in the product ID, and then return a response entity of noContent.build. As usual, we will create the methods under the interface and the implementation class. This method will fetch the product using getByReferenceID and then call repository.delete. By running the server and navigating to our Angular application, we could test the delete functionality. It should work just fine. If you want to experiment, you could enable the debug mode and you could test what's happening under the delete product. Currently, it should be creating two different sessions, one for fetching the product and another transaction to delete it. You could test out how annotating the delete product method with transactional annotation will allow us to execute both operations under single transaction. We have just completed the basic operations when working with Spring Transaction. In the next module, we will move on to more advanced topics. See you in the next module. Hello there. This session will be a little bit longer than usual because there's a quite bit of prep work to be done before we can dive into working with exceptions. We will set up the entities and repositories for our order page, and after that, we will implement the checkout functionality. As you can see, we can already create orders in our front-end app, but the actual checkout process is still not there. So let's jump to the IDE and get started. To place an order, for sure, we need a customer. We will start by creating a new Java class under the customer.domain package and call it customer. As before, we will annotate our class with the @entity annotation and @table with the name customer. Our entity will include a private long ID and a private string name. We will annotate the ID with the @ID annotation and the generated value with the strategy generated type.identity. Also, to keep things simple, we will store the customer's balance in a big decimal balance. We will generate two constructors, one empty and the other one with all the fields excluding ID. And as usual, we will generate getters. You will notice that in this lecture, we have a lot of repeating stuff, creating entities, repositories, and services. But from the next lecture onward, we will not be creating any new entities or repositories, and we will focus more on the interesting stuff. So, with the customer entity in place, under the customer.repository package, we will add customer repository interface that extends GPA repository with customer and long. This will give us all the basic CRUD operations. To keep things simple, for now, we will access the repository directly from other services. We will define the order entity in a new package called order.domain. We are keeping the domains separated, although later we will be accessing the customer repository from order service, which is not recommended, but it will be acceptable for this example. Just like before, we will annotate our class with the addEntity annotation and addTable annotation. For the table name, we will use orders. We want to avoid using the MySQL reserved word order. Our entity will include a private long ID, a customer referencing the newly created customer object, a private string currency, a private instant, order date, and private big decimal total amount. We will annotate the ID with the ID annotation and the generated value with the strategy generated type.identity. Since multiple orders can belong to a single customer, we will annotate the customer field with the many-to-one annotation with the fetch type lazy and a join column with the name customer_ID. For the currency field, we will use the add column annotation with the length of 3 and nullable false. We will not annotate the order date and the total amount explicitly. Hibernate will map them automatically using the camel case, and we can confirm this by checking the generated table structure in the database. We will also generate an empty constructor and one more that takes all the fields except the ID, along with the getters for all the fields. Every order contains items. So, let's now create the order item entity to represent those. As usual, we will add the addEntity annotation and table with the name order_item. This class will include a long ID with the addID annotation and generated value generated type.identity, a reference to the order with the many-to-one annotation and fetch type lazy, and add join column annotation with the name order_ID. Then we will add a product field referencing the product object, a big decimal unit price capturing the price at the time of the order to avoid changes affecting historical data, a private int quantity, a private big decimal line total, which represents the unit price multiplied by the quantity. It's time to annotate the remaining fields. The product field will get a many-to-one annotation with fetch type eager, assuming we need the product details every time we load an order item. Also add the @join column with the name attribute product_ID. For the unit price, we will add the @column annotation with the name unit_price. For the quantity, it will take the @column annotation with nullable equal false. For the line total, we will add the @column annotation with the name line_total and nullable false. Finally, we will generate two constructors, one empty and the other one with all the fields excluding ID. And as usual, we will generate getter methods for our fields. Now that our entities are ready, let's move on to the controller. Under the order.controller package, we will create a new class called orderController. We will annotate our class with the REST controller annotation and a request mapping with /orders. We will define a checkout method using the post mapping and take in a request body of type checkout payload. Let's create the checkout payload class under the order.payload package. This class will include fields with some hard-coded values for now, just for simplicity. It will have a private long customer ID with the value 1, a private string currency with the value euro, a private instant order date with the value instant.now, and finally a private list checkout item payload items. we will define the checkout item payload as a record in the same package. Our record will have a long product ID, a big decimal price, and an int quantity. Back in the checkout payload, we will add getters for all fields. Navigating to the order controller, we will call orderService.checkout and pass in the payload. We will define the order service as a final field, and let's now create the order service interface under the order.service package and implement it as order service impl class under the impl subpackage. Our implementation class will be annotated with the @service annotation. Back to order controller class, we will see a warning. It's complaining about the missing order service bean. We will fix the issue by injecting it through the constructor. Then we will generate the checkout method and implement it in the order service impl class. To calculate the total amount of the order, we will stream over the items, map each one's price multiplied by its quantity, and reduce the result using bigdecimal.0 as a starting value. Next, let's create the order object. To be able to create an order object, we need a reference for the customer, which is missing at this point. So we will inject the customer repository using constructor injection. We will fetch the customer using customer repository.getReference by ID. Then pass the customer payload.currency, payload.orderdate, and total amount into the order constructor. To save the order, we will introduce the order repository interface under order.repository package. It will extend the GPA repository with the entity order and ID type long. Now we can inject the order repository into order service impl class and call order repository.save and pass in the order. We should annotate the checkout method with the transactional annotation to ensure that transaction is properly managed by Spring. For now, we will comment that out. We will revisit this later once we explore the exception behavior in transactions. To save the order items, we could rely on Hibernate with one-to-many mapping with Cascade enabled, but we will do it manually here on purpose to better understand exception handling. We will start by creating the order item service interface and its implementation. As usual, we will add the service annotation to our service class. Also, it's recommended to drop the public access modifier from the implementation class. In the order service impl class, we will inject the order item service using constructor injection, then call order item service.create order items, passing in the order and the payload.items. Then generate this method in the interface and implement it in the order item service impl class. To validate the product IDs, we will extract them from the list by creating a set of long product IDs and assign the value of items.stream.map checkout item payload and get the product ID. Then we collect the results with the collectors.toSet. Using the product repository, which we inject using the constructor injection, we will call findAll by ID and pass in the product IDs. We will compare the size of the returned products with the original set of IDs. If they don't match, that means some of the product IDs are invalid. In that case, we throw a custom unchecked exception, invalid product ID during checkout exception. We need to generate this exception under the order.exception package, extending runtime exception. Because runtime is unchecked exception, we don't need to handle it explicitly. But if we had extended the exception instead, the compiler would have forced us to either catch or rethrow the exception. We will look into that in more details later. Let's go back and stick with the runtime exception for now. To be able to quickly map a product ID to the product object, we will convert our products to a map by defining a map of key long and value product. Let's call it product map and assign it the value of products.stream and collect collectors.toMap with the key product.getID and value functionality.identity, which stand to the product object. Finally, we map each checkout item into an order item object, setting the order product quantity and calculating the line total by multiplying price by quantity. Then we collect them into a list. To save the order items, as you may guess, we need order item repository interface, extending GPA repository with the order item as entity and long matching our ID type. Let's inject the order item repository to our order item service impl class and call save all, passing in the order items. With that, the checkout functionality is fully implemented. Along the way, we introduced checked and unchecked exceptions. And just as a quick recap, checked exceptions extend exception class and must either catch or declare the exception. On the other side, unchecked exceptions extend the runtime exception and don't require explicitly handling them. In the next lecture, we will look into how transactions behave differently based on the type of exception being thrown. See you in the next lecture. Hello there. In the previous lecture, we implemented the checkout functionality, but until now, we could not test that yet. So let's open the IDE, add some breakpoints in the checkout method, and run our server in debug mode. Before triggering the checkout, we need to ensure a customer with ID 1 exists. So let's navigate to the database section, refresh the table list, and locate the customer table. We need to add a new row with the balance 100 and name new customer. Alternatively, we could use MySQL console to insert the new customer by running the query insert into customer, name, balance, values, new customer, and 100. Now we could test the checkout functionality. From the Angular application, select few items and hit the checkout button. When we reach the breakpoint, we observe that the method is not annotated with transactional annotation. So a new transaction is started for each repository call. Proceeding with the breakpoints, we see that the order got saved and committed to the database before order items got created. Checking the database, we can confirm that the order has been persisted. If we release the breakpoints, we can see that the order items also get persisted. What happens if an exception occurred while saving the order items? Let's simulate that by sending a request with an invalid product ID. From Postman, we can send a checkout API request with invalid product ID. Following the same flow, we hit the breakpoint. We calculate the total amount and save the order. Checking the database again, we can see the second order get created. As we proceed further, we reach the validation logic, where product size is compared to the product IDs.size. Since they don't match, an invalid product ID during checkout exception is thrown. Currently, this exception has a null message. We can improve that by adding a custom message invalid product ID provided during checkout. Even though the exception being thrown and order items not being created, the orders table still contains the second order. This happened because the order and order items operations are not wrapped within the same transaction. If an error occurred, the earlier operation will not roll back, resulting in partial data persistence. Our implementation violates the principle of atomicity, where either the entire checkout process should be persisted or nothing at all. To fix this, simply annotate the checkout method with the transactional annotation. Now, rerun the server and repeat the same API call. In the console, we can see that the transaction is rolled back. Next, let's try another checkout and observe the transaction behavior in the console. A single transaction is started for the entire method. Calls to getReferenceById, orderRepository.save, and saveOrderItems all participated in the same transaction. Even though createOrderItems lives in a separated class, it joined the same transaction. We can verify that by checking the session implementation ID in the logs. Notice that the transaction isn't committed immediately after saving the order. Once the exception is thrown, the entire transaction rolls back. Checking the database confirmed that neither the order or the order items were saved. Because we are throwing runtime exception, Spring rolls back automatically and preserves the data consistency. So, what would happen if we throw a checked exception instead? Let's modify our exception class to extend exception instead of runtime exception. Then propagate the exception to the order service, then the order controller. When we repeat the same test, the same exception is thrown, but this time the exception being committed instead of rolled back. Once again, we see the same inconsistency in the database. This happened because Spring doesn't roll back automatically for checked exceptions. To ensure rollback in these cases, we need to explicitly configure the rollback behavior in the transactional annotation. Understanding how checked and unchecked exceptions affect transactions is critical. In the next lecture, we will dive into how to control the rollback for each of those exceptions. See you in the next lecture. Hello, and welcome back. In this lecture, we will cover two things. First, we will improve our test data by reinitializing our data every time we restart the server. This will make debugging easier and more predictable. Then, we will dive into how to control transaction rollbacks. This will give us a full control on how our application will react to specific exceptions. From our IDE, let's modify a few lines under application.yaml file. Under Spring GPA Hibernate, we will update the DDL auto from update to create. Then, under Hibernate, we need to add database platform org.hibernate.dialect.mysql dialect. Also, differ data source initialization and set it to true. We need to command Spring to initialize our data every time it starts. We can achieve that by setting sql.init.mode and set it to always. Let's add data.sql file into resources directory. You will find this file provided in lecture resources. Spring will automatically pick up this file and execute all the queries inside our file whenever the application restarts. It will create a single customer, 2 categories, and several products, making it easier to work with our data each time we restart the server. To test if the data initialization is working as expected, let's restart the server and navigate to our database. Let's verify by checking the tables. The category should have 2 entries, and both order and order item should be empty, and product table should have 8 products. Also, we could do a quick test by navigating to our Angular application and ensure everything is still working as before. Now that we have more consistent data, let's talk about how to control transaction rollbacks. Suppose we want our transaction to roll back whenever we encounter our custom exception. As we already covered, Spring doesn't automatically roll back for checked exceptions. So, we need to explicitly tell Spring to roll back for our exception, which we can achieve by adding the rollback for attribute and pass in our custom exception. To test this, let's start the server in debug mode, and using Postman, we will trigger the checkout API. Once we reached the createOrderItems method, in the console, we will see a confirmation that it participated in the existing transaction, and when an exception occurred, the transaction rolled back. This is exactly what we expected. The transaction is rolling back even for our checked exception. Next, let's examine noRollback4 attribute. As the name indicates, we use this attribute when we want to prevent an exception from rolling back the transaction. both attributes accepts a single exception class or even an array of exceptions using the curly braces. To illustrate this, we will update our custom exception to extend runtime exception. Also, remember to remove the rollback for attribute to avoid unexpected behavior or conflicts that could vary based on the Spring version you are using. Let's restart the server, and from Postman, let's trigger the checkout API call. Skipping through our breakpoints, we will see the same exception thrown just as before, but this time the transaction would not roll back. In this lecture, we covered how to control if an exception should roll back or not to roll back a specific transaction. In the next lecture, we will dive deeper into Spring transactions by covering propagation types. See you in the next lecture. Hello there. In this section, we will cover transaction propagation, one of the core ideas behind how Spring manages transactions. So, if a method annotated with transactional annotation calls another method, Spring needs to decide how to handle the current transaction context. Should the second method join the existing transaction, create its own, or execute in non-transactional context at all? Spring provides multiple propagation types. Let's dive right in and explore each of them. We will start by removing the no rollback for attribute from the transactional annotation. Then we will make sure the create order items method is annotated with transactional annotation. Let's add breakpoints for both methods and run the server in debug mode. From our Angular application, we can pick some random items and hit the checkout. As we trace through the flow, we see that both checkout and create order items share the same transaction. They are using the same session ID. The first database call in create order items simply joined the existing transaction. The same thing happened during the save all operation. And the transaction only commits once both operations are done. That's because required is the default propagation setting. If a transaction already exists, it joins the existing transaction. Otherwise, it starts a new one. We could specify it explicitly using the propagation and assign it propagation.required. But it behaves the same way since it's the default propagation type. Let's try changing the propagation type to requires new. With this setting, Spring suspends an existing transaction and starts a completely new one for the annotated method. Let's restart the server, go back to our Angular application, and check out a single item. In the logs, we will see that checkout still uses the default propagation.required with a session ID ending in 109. When save order items get triggered, Spring notices there's an existing thread-bounded session. It suspended that transaction and started a new one with the name matching our method name with a different session ID. If we watch the logs closely, we will see that everything inside create order items happens in the new transaction. And since each transaction commits when the method finishes, create order items try to commit before checkout is done. Because of that, the new transaction cannot see the uncommitted order entity. So the method stalls. It's trying to use the order entity which hasn't been persisted yet. This is why requires new need to be used carefully. It's great when we need a clean, isolated transaction, but it becomes tricky if the new transaction depends on data from the outer one. So what would happen if we considered passing the order ID instead of the full entity and tried to fetch the order inside this method? It would not work because the outer transaction hasn't committed the order and it doesn't exist in the database. Always remember, different transactions run completely in isolation. Our next item from the list is mandatory. This one requires a transaction to already exist. If there's no transaction, Spring throws an exception. To see this in action, we can comment out the transactional annotation on this checkout method. We restart the server, and from the Angular application, we either place the same order again or create a new one. Here's what happens. Each part of the checkout method creates its own transaction. But when we execute the order item service.create order items, Spring throws an exception. No existing transaction found for a transaction marked with propagation mandatory. This is actually the behavior we want for the create order items. We want to make sure it's always part of the same transaction as the order creation. Either both of them succeed or none. So let's bring the transaction annotation back, restart the server, and retry the failed order. Now we see that both methods participated in a single transaction again, and everything goes through smoothly. We can check the database and verify that the order item was successfully persisted. Next up is the supports propagation type, which is a bit more flexible. It joins an existing transaction if present, but it never creates its own transaction. However, this isn't the same as omitting the transactional annotation. Hibernate may still reuse this session, which can impact things like lazy loading and dirty checking. So it's important to use this mode carefully. In our case, since checkout is already transactional, create order items will just join that transaction. You can pause here, run the server, and debug it. Next on our list is nested. This propagation type introduces save points. It allows partial rollbacks within a larger transaction, as we covered earlier. The issue is not all transaction managers support it. Try restarting the server and checking out any item. In the IDE, you will likely see an exception that the GPA dialect does not support save points. That's our signal that nested is not available in our setup. The next propagation type is never. As the name implies, this one completely avoids transactions. If there's already an active transaction, Spring throws an exception. Let's fire up the server again and place a new order. When create order items get executed, Spring throws an exception. Existing transaction found for transaction marked with the propagation never. This kind of setup makes sense for actions that should never be part of transactional context. For example, when generating reports or doing some heavy lifting in the background. Finally, we come to the last propagation type not supported. This one suspends the current transaction and runs the method without any transactional context. Once the method finishes, the original transaction resumes. We can restart the server and do another checkout. Everything looks fine until we try to persist the order items, and then it stalls just like with the requires new. That's because the main checkout transaction is suspended and we are trying to work with data that doesn't exist yet in the database. At this point, it makes sense to switch create order items back to mandatory. Always consider the impact of each propagation type and align it with how the system should behave. See you in the next lecture. Hello there. In the previous lecture, we explored propagation types and how they influence the transaction context a method will run in. In today's lecture, we will dive into transaction boundaries and how they also decide if a method will execute within the same transaction or in a new transaction. Since boundaries are depending on threads, let's first define what is a thread. A thread is a simple one-path execution inside your program. Imagine the program as a to-do list, a single thread representing a single person working through that list item by item. If the program starts more threads, it's like adding extra people, each handling their own item from the list so that tasks can run in parallel and we could finish the work faster. So, how this relates to what we are doing? When HTTP request hits our endpoint, a single thread handles the execution, and everything that thread does sits behind a single transaction boundary. until we tell the program to move some work into another thread. Let's see the impact of having multiple threads on our transactions. In our IDE, navigate to Create Order Items method and annotate it with async annotation. This simply commands our method to execute in a separated thread. In Spring, to activate the async annotation, we need to enable it by adding Enable Async Annotation either in a dedicated configuration class or in Spring Boot application main class. Next, start the server and navigate to our Bit and Byte app. Let's perform a checkout. Back in the IDE, our code hasn't fundamentally changed, except we're executing the create order items asynchronously. As expected, this leads to an exception because created order items is annotated with the propagation.mandatory, which means it must run inside an existing transaction. But since it's now executing in a separated thread, it's no longer share the same transaction context. By definition, a transaction is always bound to the thread that started it. When a code runs in different thread, it effectively runs in a different transaction. Before we resolve the issue, since our exception extends runtime exception, we don't need to declare it in our method signature or explicitly handle it. So let's remove the throws declaration from our methods to keep the code cleaner and more concise. To resolve the exception, we can try by removing the propagation.mandatory. After restarting the server and performing a checkout again, we noticed that by the time create order items start executing, the original transaction has already completed and committed to the database. This happens because asynchronous execution runs in parallel on different threads, and it doesn't block the original transaction from completing and committing their changes. We can verify that by checking our database. The order items table is still empty, while the orders table already contains the new entry. When we resume execution, the insert into order items executes successfully and commits to the database. But there's a big issue. This query succeeded only because we paused execution using the debugger. Normally, it would throw an exception since the order hasn't been committed yet, as we will see at the end of this lecture. What if an exception occurred while persisting the order items? To test this, from Postman, we can trigger a checkout with invalid product ID just as we did previously. Clearing the IDE console and stepping through the debugger, we observe that the initial transaction has already committed, meaning rolling back the transaction is impossible. The validation throws invalid product ID provided during checkout exception, and upon checking the database, an order entry with ID 2 exists but without any associated order items. To further highlight transaction boundaries, let's examine another scenario where the main checkout method throws an exception. We simulate that by adding the following condition. If order.getID is greater than 0, which is always true, then we throw a runtime exception with the message unexpected exception. After restarting the server and performing a checkout through our Angular application, we observe that the asynchronous method createOrderItems begin executing. However, the main method throws an exception, preventing the order from being committed. Following that, the asynchronous method also fails due to a foreign key constraint. It references an order ID that was never persisted. In this lecture, we saw how transactions are tied to threads and why it's important to be careful when adding asynchronous annotation, especially if two methods' data depends on each other. In upcoming lectures, we will discuss how to benefit from asynchronous execution without sacrificing data consistency. See you in the next lecture. Hello there. In the previous lectures, we established a solid understanding of propagation types and transaction boundaries. In this one, we will look into some common use cases where data consistency get compromised. From our IDE, let's start by removing the async annotation from the createOrderItems method. Next, let's define an interface under the notification.email.service package and call it email service. We need to implement our interface under .impl package. Make sure to annotate our class with the service annotation so that Spring recognizes it as a managed bean. We will start by declaring our method with a public void sendReceipt and pass in the order. Inside the implementation, we will call sendEmail with an order.getID and order.getCustomer.getName. We will let the IDE generate our sendEmail method. Then, we will simulate sending an email by calling thread.sleep for 200 milliseconds and wrap it with a try-catch. Since the actual implementation of sending an email doesn't make any difference, we will simulate that by simply calling system.out.println and passing the message sending receipt for the order with the order ID to customer and passing in the customer name. We will annotate our method with the override annotation and pull it to the email service interface. Back in order service impl class, we will inject email service via constructor injection. In the checkout method, we will call email service.sendReceipt passing in the order. Let's start the server in debug mode and place a breakpoint at the email service.sendReceipt. Switching over to our Angular application and try checking out few random items. As we step through the code, we can see that sending receipt message is printed to the console. This simulates that the email has already been sent. Right after that, we throw an exception. Checking the logs, we see that the transaction is rolled back. Looking into the database, the order is not created. But here's the problem. The email has already been sent. That means the customer received a confirmation for an order that doesn't exist. Absolutely, that's something we don't want in our system. So, would annotating the send receipt with async or transactional annotation help in this case? Let's try that. We will add the transactional annotation with propagation requires new, hoping it solves the issue. Restart the server and try another checkout. We will see that even though the send receipt now runs in a separated transaction, it really has no impact. And since it doesn't persist any data, it probably shouldn't be marked transactional in the first place. Before looking further for a solution, let's flip the scenario. This time, instead of the checkout method failing, we will simulate a failure in the email service. Let's comment out the exception in the checkout method and modify the logic in the email service to throw an exception whenever the order ID is greater than 1. After throwing the email service not available exception, we need to create our custom exception class. It will extend runtime exception, and inside the constructor, we will pass a custom message. Email service is not available. Restart the server and attempt 2 checkouts. On the first attempt, everything works as expected. The order is created and the email is sent. On the second attempt, the email service throws an exception, which in turn rolls back the entire transaction, preventing the order from being created. Failing the entire order because the notification system went down doesn't seem correct. In ideal world, the order persistence should be decoupled from the email service. A workaround to decouple both operations would be marking the send receipt with async annotation. But we already know what will happen. The email could still be sent even the order never gets saved. It's clear that managing transactions with traditional approaches have many limitations. When integrating with external systems like emails, Kafka, or any third-party APIs, we need to think differently. Ensuring consistency in those cases requires more advanced strategies. In the next lecture, we will look into Spring events, which allow us to build event-driven approaches, which is more robust, performant, and loosely coupled, and solves all the data inconsistency we faced in this lecture. See you in the next section. Hello there. So far, we have focused on building a solid foundation in Spring Transaction Management. That workaround was essential because real-world applications don't just manage data, they react to events. Event-driven design is a natural extension of transactional thinking, and understanding how events interact is a key to build robust and decoupled systems. Let's begin with a traditional example where a customer is creating an order. Initially, the process involves the order service directly referencing several other services. For instance, it interacts with the email service to send a confirmation email and the shipping service to arrange the product delivery. Also, if we need to deduct the order cost from the customer account, the order service needs to directly interact with account service. This direct referencing creates a significant coupling among services. The order service must explicitly know the details about each related service, including their methods and parameters. Furthermore, as previously discovered, this type coupling can lead to data inconsistency, in particular when multiple services interact asynchronously. This is precisely where Spring Events offer a significant advantage. Instead of tightly coupling the order service with all related services, we shift our approach. When something significant occurs, like an order creation, the order service simply publishes an event. Interested services such as email service, shipping service, and account service independently listen to those events. Adopting an event-driven approach helps ensure data consistency and serves as an essential building block to transition toward microservices architecture, where switching from Spring Events to advanced message solutions like RabbitMQ or Kafka becomes straightforward. Initially, working with event-driven approach may seem challenging or even counterintuitive, but rest assured, I will guide you carefully through the concepts, exploring various examples step by step and addressing how this approach solves the inconsistency in data we faced earlier. See you in the next lecture. Hello there. In Spring, there are two primary ways to listen to events: the event listener and transactional event listener annotation. While both annotations handle application events, they serve different purposes, especially when it comes to transaction management. To start with the event listener, from our IDE, under the customer.service package, we will create a new interface called customer service and implement that interface under the impl package. Note that we are oversimplifying by storing the customer balance under the customer entity, but it's better to keep the course focused on transactions. We will annotate our service implementation using the service annotation, then inject the customer repository using the constructor injection. Let's have a method that deducts from the customer balance by declaring a public void deduct from balance, which takes a long customer ID and a big decimal amount. We need to annotate our method with the override annotation, then pull our method into the interface. For the implementation, we will start by fetching our customer from the customer repository using the findById method, passing in the customer ID, or else throw an exception if the customer is not found. We will check if the customer.getBalance and compare it to the amount is less than 0. That means the customer balance could not cover the order. In that case, we throw a new exception, insufficient balance exception. We need to create our custom exception under the customer.exception package. Let it extend the runtime exception and generate an empty constructor with a static method account has insufficient balance. Back in our deduct from balance method, we will call the customer.deductAmount. Since this method doesn't exist yet, we will generate it. To set the new balance, we will assign this .balance to equal to the current balance and subtract the order amount from it. Since our operation updates data, let's wrap it with a transactional annotation. Next, we will navigate to the order service implementation class and inject our customer service using constructor injection. Inside the checkout method, we can call customer service.deduct from balance, passing in the customer.getID and the total amount. To handle events in various scenarios as promised, we will add another class that simulates having a WebSocket that notifies our Angular application once an order is created. Similar to email service, we would not dive into WebSocket implementation. Instead, we will simulate the implementation by logging to the console. Since the main idea is to understand how events react in different scenarios and how to maintain consistency. To do that, under the notification directory, let's create a WebSocket.service.WebSocket service interface. Then implement it under the impl package. We need to annotate our implementation with the service annotation. We will start by declaring our public sendOrderCreated notification, which takes an order ID of type long. We will simulate sending a notification by forcing our thread to sleep for 200 milliseconds. Then, we will surround our call with a try catch. Finally, we will call system.out.printf, passing in the message WebSocket sendOrderCreated notification for the order with ID, passing in the order ID. Then, we need to annotate our method with the override annotation and pull it to the WebSocket service interface. Although the implementation is so similar to the email service, they behave differently from the business perspective, as we will see shortly. In the checkout method, we will call WebSocket service.sendOrderCreated notification, passing in the order.getID. So far, we have followed a traditional approach with no events involved to illustrate the exact changes required if you are refactoring your legacy system. Before starting the conversion to event-driven approach, let's quickly run the server and verify our current implementation. Checking out the order, we will see the order creation, a balance deduction with the value 26.7, and both email and WebSocket notification being sent. Verifying the database confirms that the order and order items entries are created, and in the customer table, the total amount of the order was deducted from the initial value 100. In the email service impl class, to avoid long waits, let's decrease the thread.sleep time to 200 milliseconds. Since the implementation is working as expected, we can convert our application to event-driven approach. First, to publish events, Spring provides application event publisher, which we can inject into our class using the constructor injection, same as we did with our services. Let's remove the references for customer service, email service, and WebSocket service. Also, remove them from the constructor. In the checkout method, we will keep the service-related calls commented just for reference. To publish events, we need an object to represent the published event. It's recommended to create a data transfer object specifically for the event and avoid using existing DTOs or domain entities. Under the order package, create a new event package with a record order created event. Our record will have a long order ID, long customer ID, and a big decimal total amount. It's time to publish our event. From the checkout method, we will add application event publisher and call publish event, passing in a new instance of the order created event with the parameters order.getID, customer.getID, and total amount. Simply adding this line, we have our event published, but until now, we don't have any listeners. Let's create our first listener under the customer.listener package and call it customer order created event listener. Notice that I included the domain name customer in the listener class name, so it becomes easier to distinguish them later. We annotate our listener with the add component annotation since there is no more suitable annotation in this case. We will start by declaring a public void method and call it handle, since it's a naming convention when handling application events. Then we will pass the order created event as a parameter. After that, to declare our method as a listener, we need to annotate it with the @EventListener annotation. With this simple implementation, Spring will take care of triggering our method whenever the order created event is published. For the implementation, we will simply delegate our call to the customer service. So let's start by injecting the customer service using constructor injection, then call customer service.deduct from balance, passing in the event.customer_id and event.total amount. Let's do the same for the WebSocket notification, creating a listener called WebSocket order created event listener under the notification.websocket package. Annotate our class with the component annotation, then we will declare our method and annotate it with the event listener annotation. Then, after getting access to the WebSocket service, we will call WebSocket service.send order created notification, passing in the event.order_id. Lastly, we will create email order created event listener under the notification.email.listener. Again, annotate the class with the component annotation and implement the handle method. After injecting the email service, we call email service.sendReceipt. But this time it requires a full order entity, and from our event we have the order ID only. I did it this way to show you how we can refactor a legacy code with minimal changes. So, let's inject our order repository using constructor injection, fetch the order by calling order repository.findById, or else we throw an exception. Then we can simply pass the order to the sendReceipt method. We will add breakpoints to both email and WebSocket listeners. Back to our checkout method, the IDE provides a quick way to view all the listeners for a specific event. We can click on the customer one to also add a breakpoint. With this implementation, we have achieved the decoupling we are looking for, which make it easy to add a new listener in the future with zero changes to our order service. Let's quickly verify the application still functions as expected. Check out an order, then following the breakpoints, it confirms that the event is captured by each listener, the balance is deducted, email sent, and WebSocket notification is delivered. And from the database, we can confirm our entity were persisted correctly and the order amount was deducted from the customer balance. In the next lecture, we will dive deeper into event listeners by exploring the conditional event listeners and how to enforce execution order. See you in the next lecture. Hello there. In this lecture, we will cover conditional event listeners. Let's say we received a new requirement from our stakeholders where every order above 50, the customer will automatically receive 5% of the total amount as a credit, which they can use only in future orders. From our IDE, let's clean it up a little bit by removing the commented code. After that, since we're already publishing an event whenever a new order is created, we can leverage that. We can either create a new listener or extend our existing customer order created event listener by adding a new method and call it handle large order. This method will also listen to the same order created event, so we will annotate it with the event listener. For the implementation, we will delegate the call to customer service.createBalance, passing in the customer ID and the total credit amount. We will generate the method, improve the parameter names a bit, and then implement the logic. First, we need to fetch the customer. We can reuse the logic from deduct from balance method. Once we have the customer, we will call customer.credit passing in the amount, which will simply add the credit amount to their existing balance. Since we don't want to trigger the listener on every order, but only when total amount is greater than 50, we can make the event listener conditional. Spring supports this via the condition attribute, which accepts a Spring expression language known as spell, and assigns the value of event to total amount and gets the double value, then check if it's greater than 50. Let's start the server, and from our Angular application, we will check out an order with a total less than 50 to verify that the handle large order method doesn't get triggered. As we can see, our method wasn't triggered, and the condition is working as expected. So let's check out another order with a total amount greater than 50. In the console, we have an exception, since the customer balance cannot cover the total order amount. So, to reset the customer balance, the easiest way is to restart the server, then the balance reset back to 100. Let's check out the failed order. We see that the first handler get triggered and the second listener also get triggered. That proves our condition is working as expected and only getting triggered if the total amount exceeding 50. Note that we have a bug in the logic. We are crediting the full amount instead of multiplying the total amount by 5%, which we will fix in later lectures. We demonstrated how easy to achieve conditional event listeners and how powerful they are. Since the event is always published, but each listener decides whether to react or not to react based on a condition. We will also cover one additional important aspect. By default, Spring doesn't guarantee the order in which event listeners get executed. Let's take this scenario. Imagine a customer with insufficient balance trying to place an order above 50. If we apply a 5% credit before validating their balance or deducting from the order amount, they could successfully place the order using that credit, which would clearly violate our product requirements. This is why controlling listener execution order becomes critical. We want to ensure that the balance validation and deduction happens first, and only after that we should apply any promotional credits. To enforce the order, Spring allows us to use the order annotation on listener methods. Lower values have higher precedence, so we can annotate the balance deduction listener with value 1 and the credit method with order with value 2. However, for now, we will set the handle large order to -1 so that it runs before the balance and we can see a difference from our previous debug. Let's restart the server and using the bit and byte app, randomly add pizzas until the total goes beyond 50. Then we will check out our order. You will see that the handle large order getting triggered first, confirming that the order annotation is working as expected. We just covered two important concepts, the condition and the order, to have more control over the event listeners. You will probably use them a lot, especially when refactoring legacy code. In the next lecture, we will circle back and check how using event listeners impact transactions. See you in the next lecture. Hello there. Until now, we barely scratched the surface of Spring events, especially when it comes to how they behave inside a transaction. In this lecture, we will dive further and explore what would happen if an exception is thrown within event listener. Let's head over to the IDE and take a look at the checkout method. Everything until line 51 is executed inside the current transaction. Here, where things might get a little bit tricky. In previous lectures, we agreed that throwing a runtime exception causes the transaction to roll back, while throwing a checked exceptions usually doesn't roll back the transaction. But the behavior changes when exceptions are thrown from inside event listener, and we are about to see why. First, we will simulate an exception inside the WebSocket service implementation class. Right inside the method, we will check if the order ID is greater than 1. In that case, we will throw a custom checked exception. Let's generate our custom exception under the exception package and call it WebSocket handled exception. Our class should extend the base exception class. Inside the constructor, just call the parent constructor and pass in a static message handled exception. Now that we defined our exception class, we need to make a few updates. Since it's a checked exception, we will add the exception to the method signature. Then do the same to the interface, and also don't forget to add it to the WebSocket order created event listener. Once we updated all the method signatures, we restart the server to test our application. From the Angular frontend, we will place our first order. It will go through just fine. You will see the listeners being called, no exceptions are thrown, and the transaction commits. Now place the second order, and we know this time the order ID is greater than 1. You will notice we hit the same breakpoints as before. First, the customer balance listener, which completes successfully, then the email listener, which also runs without issues, and finally, we reach the WebSocket order created event listener. This time, since the order ID is greater than 1, our exception gets thrown. In the logs, Spring reports that the WebSocket handled exception was thrown, and then you will see that the entire transaction is rolled back. So, in this case, the checked exception rolled back the transaction. Let's trigger the checkout one more time and debug what is happening. When the exception is thrown, we see the application listener method adapter. Inside this class, it handles the exception differently based on its type. If the exception is instance of runtime exception, it just throws the exception directly. But if it's a checked exception, in that case Spring wrap it inside undeclared throwable exception. Let's check the undeclared throwable exception. We can see that it extends runtime exception, which means even though we threw a checked exception, Spring treated it as unchecked exception, and that's what triggered the rollback. So, why Spring do that? Simply because of decoupling. The whole point of events is to loosely couple our classes. Imagine the publisher class had to handle dozens of specific exceptions from each listener. That would totally break the point of using events. By wrapping the exceptions, Spring let the errors bubble up without forcing a tight coupling between the publisher and the listener. If you don't want the failing WebSocket to fail the whole order, you need to handle it yourself. You can do that by adding a try-catch block inside the listener. A small modification to avoid triggering this exception in future, we will update the condition to be greater than 5. So, let's zoom out a little bit and think about our logic. We need our order to roll back if we fail to deduct from the customer balance, but we don't want it to fail if sending the email or WebSocket notification had an exception. Also, we need the email and WebSocket notifications to trigger only if the order was saved successfully. The best way to do that is by using transactional event listeners, which we will cover in the next lecture. Hey, in this lecture, we will cover the second type of event listeners within the Spring framework, which is the transactional event listener. The name itself might be misleading. It may appear that the listener will execute within a transaction, but actually it's not the case, as we will see in this lecture. From the IDE, we will add a console log at the very end of the checkout method, something simple like system.out.println, passing in a static message reached the end of the method. This will help us mark exactly when the method finished execution. Go ahead and run the server. And from our Angular application, let's try checking out few items. The event get published, and the listeners are triggered before the hit of the final system.out.println. Then, only after that, the transaction is actually committed. That's a red flag. What is happening here? We are publishing the order created event before the order actually persisted to the database. So, If the transaction fails for any reason, we might have already sent out the email and notified other systems, even when the order was never created, as we saw in previous lectures. Fixing this issue is pretty straightforward. In the email order created event listener class, we change the annotation from event listener to transactional event listener. This ensures the listener will only get triggered after a transaction successfully commits. Don't confuse the name transactional event listener to mean that the listener itself runs inside a transaction. It means the publisher of the event runs within a transaction. Let's test this change. Fire up the server and let's place a new order. Once the event is published, we see our custom message printed first, then the transaction commits, and only after that the email listener is triggered. That's exactly the behavior we are looking for. If we check the database, the order is already committed by the time the listener is triggered. 3 main points to highlight here. Since our method is annotated with the transactional event listener, it will never get triggered unless the checkout method successfully commits. The second point, we can safely fetch the order details in any transaction, because everything is already persisted to the database and data will be visible to other transactions. Lastly, any exception thrown from the listener or anything that follows would not roll back the transaction, because the data is already persisted and it's not possible to roll back already committed data. So let's check out another order. This time in the console we see an exception. Email service is not available. Exception being thrown because inside the email service implementation class we throw an exception if the order ID is greater than 1. But the transaction is committing and didn't roll back exactly as expected. Checking the database, we confirm the 2 orders are created successfully. Since it's working as expected, we need to implement the same logic to our WebSocket order created event listener. Just like with the email listener, switch the annotation to transactional event listener, and now our logic aligns perfectly with our business needs, where send email and WebSocket notification listeners don't get triggered unless the order successfully persists to the database. Also, if an exception occurs within those listeners, it will not roll back the order transaction. You might be wondering why this triggers only after commit, and can we control that? The short answer is yes. The transactional event listener annotation has a phase attribute. By default, it is set to after commit, which is why it fires post commit. But there are other phases too, like before commit, after completion, and after rollback, which we will cover in the upcoming lectures. See you in the next lecture. Hello there. In the previous lecture, we used the transactional event listener with the default after commit phase. In this lecture, we will dive into the second phase, which is before commit, and check when it makes sense to use it. From the IDE, let's navigate to the WebSocket or the created event listener and change the transaction phase to before commit. What is the impact of this change? The first thing to notice, since the listener is now triggered before the transaction is committed, any exception thrown from inside the listener will cause the entire transaction to roll back. Another common question that comes up here, if the transactional event listener can roll back the transaction, how it's different from the event listener. The difference is all about when the listener gets triggered. With the event listener, the method is triggered immediately after the event is published, regardless of the transaction boundaries. While with the before commit, the listener runs only after the publishing method finishes executing and after the transaction completes, but just before the transaction commits. And by default, it only works when the publishing method is a part of an active transaction. To see this in action, let's start the server and add a breakpoint inside the listener. From the Bit and Byte app, we can do a checkout. Notice that the event gets published, but the listener don't get triggered right away. After the main method finishes and as the transaction completes, that's when our method runs. Then, after the method annotated with the before commit finishes, the transaction commits. And finally, the after commit listeners like email service get triggered. Let's try another checkout, this time forcing an exception from the WebSocket service. The transaction gets rolled back exactly as we expected with the before commit. This shows us how much control we have over the transaction behavior and listener phases. In the next lecture, we will explore the remaining two phases. See you in the next lecture. Hello there. In this lecture, we will assume we have an inventory which gives us how many doughs we have available to make pizzas. If a customer ordered more pizzas than what we have, the order should fail. This scenario is more common in product-based websites like Amazon, but it's perfect to illustrate the remaining two phases that we didn't cover yet, the after completion and after rollback. We will start by creating a new inventory service interface under a new directory inventory.service. As usual, we will also implement the interface under the impl subpackage. The service class is annotated with the service annotation, and we will add a public void method, check availability, and reserve. It will take a UUID, order UUID, and a list of checkout item payload items. We will iterate over our items, and for each item, we will get the available quantity by declaring it as an int. We will assign this value from this.getAvailableQuantity, passing in the item.productID. For the implementation, we will assume we are fetching the available quantity from the database and always return a static value 10. Back to our implementation, we will check if the item.quantity is greater than the available quantity. In that case, we throw a new out-of-stock exception. We will create our new exception class under the exception package, extending the runtime exception, and within the constructor, we will pass a static message product is out of stock. Back in the inventory service impl class, if no exception is thrown, we reserve the product by calling the reserve method, passing in the order UUID, item.productID, and item.quantity. After generating the method, we will enhance our parameter names, and then for the implementation, we will assume we are submitting this call to the database. But we will do it by just printing to the console a static message, successfully reserved the number of the units of the product with ID, passing in the ID for order, passing in order UUID. Now that the logic is complete, we can annotate our method with the override annotation and pull the implementation to the interface. And since we assume this method writes to the database, we will add the transactional annotation. In the order service impl class, we will declare a reference to the inventory service and inject it using the constructor injection. In the checkout method, before creating the order, we need to check out the availability and reserve the products by calling inventory service.checkAvailability and reserve, passing in order UUID, which we can obtain from uuid.random_uuid, and then pass the variable as a parameter and also pass the payload.getItems. Let's pause a little bit and think about the implementation. The checkout method is wrapped with a transaction. Then the inventory service call will participate within the same transaction. The problem with this approach, if multiple customers try to reserve pizzas at the same time, they will read the same value from the database. Let's assume we have 2 doughs only. Each customer may end up ordering those 2 pizzas, but at the end, we will be ordering more than what we have available. That's because we only committing after the whole checkout is processed. Instead, to avoid this scenario, we will change the propagation type to propagation.requires_new. This way, the method runs in its own transaction and commits immediately independent of the parent transaction. A quick thing to highlight here, if we try to put the transactional annotation with propagation_requires_new directly on the reserve method, your IDE will complain. That's because Spring requires a method with transactional to be overridable, so it's not possible to place it above a private method. What if we change the method to public or protected? Will it open a new transaction? Let's run the server and debug this critical scenario. After checking out few items from the Bit and Byte app, you will see the checkout transaction is suspended and a new transaction is started for the check availability and reserve method. Step through the breakpoints. The reserve method is called, but it didn't open a new transaction, even though it's annotated with the requires_new. This is a local method call within the same class, so Spring doesn't go through the proxy and doesn't recognize the annotation. In this case, I will comment out the annotation and revert back the access level to private. If you wanted each loop iteration to run its own transaction, don't make the service call itself by using self.reserve and calling a method from within the class but through the proxy. That's a hack that I saw multiple times, but it will make testing a nightmare. Instead, you can extract the logic to a separated service and then call reserve_product_service.reserve. Much cleaner, proxy safe, and easier for testing. Back to the breakpoint, you will see the transaction commits after exiting the method, then resumes the original transaction to complete the order creation. This works fine because there is no exception. What happens if we reserved items, then the order creation fails? We don't want to keep those items reserved forever. Let's simulate this scenario by navigating to the checkout method and uncomment the exception lines. Then restart the server, and we will check out few items. You will see the reserve logic runs, and if we had a database, the data would have been already persisted. After proceeding, we publish the event, then we throw an exception before we commit. The order transaction rolls back, but since checkout availability and reserve method runs in its own transaction, it's already committed and would not roll back. To handle this scenario, we will implement a recover from failure mechanism. Under the inventory package, create a new package called listener and create inventory order created event listener. As usual, we will annotate the class with the add component annotation, and then we implement the handle method, which will take the order created event as a parameter. We also use transactional event listener annotation, but this time with the phase after rollback. so it only triggers if the publisher of the event rolls back. Let's inject the inventory service, then we will call inventory service.releaseProducts. We need access to the order UUID, so we will add it to the order created event record. Then we can obtain the order UUID from the event itself. Let's create the method, and in the implementation, we will assume we are fetching all the products reserved by the following UUID, and after that, we can release those products. For now, we will simulate that by printing to the console, release all products reserved by the order, passing in the order UUID. Restart the server, and we get an exception, since the order UUID wasn't added to the event. We will add it, restart the server, and test one more time. After doing the checkout, step through, and you will see that after the exception is thrown, the after rollback listener gets triggered and release the products. That puts our system back in a consistent state. Lastly, let's talk about the after completion. This phase is similar to the after rollback, but it triggers in both cases if the transaction commits or rolled back. We can implement that by adding another method. Let's call it handle after completion, which listens to the order created event, and annotate it with the transactional event listener with the phase after completion. In the body, we can simply log to the console order successfully created. Try restarting the server and checking out one more time. This method will run in both cases if the transaction succeeded or failed. In this lecture, we explored how to recover from failure and how different phases help us maintain data consistency. See you in the next lecture. Hello there. In the previous lecture, we discussed how transactional event listener with the phase after rollback help us recover from failure and bring our system back to consistent state. In this lecture, we will look into edge cases where transactional event listener doesn't get triggered. Before we dive in, we need to make some modifications to our customer order created event listener. We will adjust the order of operations so that the crediting happens after deducting from the balance. This ensures that the credited amount could not be used to pay the current order. Also, we will fix the bug where the current implementation credits the full amount instead of 5%. Let's fix that by multiplying the total amount by big decimal value of 5% represented by 0.05. Our code is ready. Let's start the server, and from our Bit and Byte app, we will check out some items until the total exceeds $100. Remember, that's the customer balance we configured in our database. When we try this, the customer service throws an insufficient balance exception. Notice that the checkout transaction gets rolled back, preventing the order from being persisted into the database. What about our reserved items? It turns out the inventory order created event listener didn't get triggered. This is one of the trickiest scenarios you will face when working with events. Since the exception is thrown from inside a method annotated with event listener, at that point, the methods annotated with transactional event listener haven't been registered yet. In short, when rollback happens, there are no transactional event listeners registered to react. In such cases, when depending on after rollback to maintain consistency, it's better to unify the listeners and use transactional event listener with a propagation phase of before commit. Let's restart the server and check out few more items. This time, the handle large order method will be executed first, since it's annotated with event listener. If we skip all our breakpoints, we can observe the following flow. The insufficient balance exception is thrown. The checkout transaction gets rolled back, but this time we can see that the after completion is triggered. Searching for the release action, we can find that the products are indeed released, confirming that the after rollback was called properly and our system is back to consistent state. As we saw, unifying our listeners helped us bring our data back to consistent state, but it's not free. Delaying our listener to the end of the method execution may have an impact on performance, especially when the listener itself throws an exception. Alternatively, we could use the Sega pattern. It's powerful and useful in distributed systems, where the Sega orchestration helps us maintain consistency across service boundaries. It increases complexity and need durable state and coordination mechanism. Understanding the trade-offs help us choose the right consistency approach for our system. See you in the next lecture. Hello there. This lecture is pretty straightforward. We will look into the last parameter in the transactional event listener, which is the fallback execution. Let's jump into the IDE and navigate to Customer Order Created Event Listener. If you check the parameters available under Transactional Event Listener, you will see few things we already covered. The phase, we already discussed all 4 phases. For the value and classes, these allow us to specify event types, useful if you want a single method to handle multiple events. Example, classes, and assign it to orderCreatedEvent.class. You can also list multiple classes separated by commas. The condition, we also covered this using Spring expression language to add dynamic conditions. It's time to focus on the fallback execution. By default, it's set to false. If you set the fallback execution to true, it overrides the default behavior where transactional event listener only gets triggered if the event is published from within an active transaction. Otherwise, it simply doesn't react. By enabling the fallback execution, the listener will get called even there's no active transaction around the event publisher. Let's navigate to the checkout method and comment out the transactional annotation. In this setup, none of the existing transactional event listener methods should fire, except the one with the fallback execution true. Run the server, and from our Angular application, try to check out few items. You will notice an exception is thrown because the order created items uses propagation.mandatory. Since there's no active transaction anymore, it blows up. We will comment out the mandatory propagation for now. Restart the server and check out the failed order. This time, you will see that only the listener with the fallback execution set to true get triggered. This option is useful when the listener needs to react to both transactional and non-transactional scenarios. However, keep in mind this feature is rarely used in practice and should be applied with caution. In this whole section, we explored Spring events by implementing real-world examples and how they help us maintain data consistency. By now, you should have a solid grasp how transactions work and how to debug tricky cases when things don't work as expected. In the next lecture, we will look into isolation level, one of the most underestimated topics in transaction management. See you in the next lecture. Hello there. In relational database, when multiple transactions happen at the same time, we can run into serious problems. Dirty reads by reading uncommitted data, non-repeatable reads by getting different results when querying the same thing twice within a transaction, phantom reads where new rows appears in the mid of the transaction. Isolation level defines how much one transaction must be protected from seeing the side effect of concurrent transactions. It's always a trade-off between data consistency and performance. Stronger isolation equals safer data but slower performance. The SQL defines 4 main isolation levels, from the weakest to the strongest. Read uncommitted. The transaction can see uncommitted changes made by other transactions. It avoids none of the problems and allows dirty reads, non-repeatable reads, and phantom reads. In the read committed isolation level, the transaction only sees committed data, so it avoids dirty reads, but still allow non-repeatable reads and phantom reads. The third isolation level, repeatable read, the transaction will see the same snapshot of the data even if other transactions modified the underlying data. It prevents non-repeatable reads and dirty reads, but still allow phantom reads in specific scenarios. The last one, serializable, the transaction is fully isolated. The transactions appear to be running one after another. It prevents all the problems and allows none. The default isolation level in MySQL is repeatable read, offering a balance between consistency and performance. We just covered the fundamentals. In the next lecture, we will start applying them on MySQL level. See you in the next lecture. Hello. In this lecture, we will dive into each isolation level and see them in action inside the MySQL console. From Docker, we will navigate to our MySQL container, and from the exec tab, we will connect to MySQL using the command mysql-u root-p, then enter the password. To check the available databases, we can use the command show databases. Let's use bit and byte. Before changing the isolation level, we need first to learn how to check the current state. To do that, prior to MySQL version 8.0, we can use select tx_isolation. If you are using version 8 or above, you will get an error. In the newer versions, the command became transaction_isolation, which gives us the session isolation level. As we can see, we got the default isolation level repeatable read. This command gives the session isolation level, but you can still explicitly define it by adding a session to the command. Instead, we can add global to get the MySQL global isolation level. At the moment, they both match because we didn't do any modifications yet. So, to be able to demonstrate isolation levels, we need two transactions running in parallel. To achieve that, we will open another terminal. From the new terminal, we will first connect to the Docker container by executing docker execute interactive terminal MySQL container and bash. Now that we are connected to Docker container, to connect to MySQL, we can run the same MySQL command. Also, change the selected database and clear the console. We will fetch the current isolation level. To change the isolation level, we will execute the command set session transaction isolation level and set it to read uncommitted. As we discussed before, this isolation level is the fastest but the least reliable, since we will be reading uncommitted data. To see that in action, we will start a new transaction. Then we will select all the records from the customer table. For now, we have a single customer. Switching to the Docker terminal, we start by disabling the autocommit and set it to 0. Then we insert a new customer by assigning the name and the balance fields the values customer 2 and 200. Rotate back to the other terminal, and remember, we didn't commit the transaction yet. When selecting all customers, we got 2 customers now. So, as we mentioned before, read uncommitted isolation level doesn't prevent concurrency issues and allow dirty reads. So, what if we now switched to the other terminal and rolled back the transaction? We know this will end up not persisting in the database. In this case, the transaction read data which was never persisted, and if we did any logic based on selected data, example, summing up the balance of all customers, or simply counting the number of customers we have, that number is not accurate. That's why you rarely see any system using the isolation level read uncommitted, unless it's monitoring the database and doesn't really care about data accuracy. We should commit or roll back the transaction before changing the isolation level, otherwise it has no effect. Time to move to our next isolation level. We can bring the previous comment back and change the type from read uncommitted to read committed. This version is slightly better, where we don't read uncommitted changes. Let's start a transaction, and same as before, we select all customers. From Docker terminal, we clear the console and then insert a new customer. Note that we are still running with the auto-commit equal false in this session. So let's have our third customer. If we switch to the second terminal and select all customers, we would not see the new customer, since it's not committed yet. Switching to the terminal inside Docker, we can commit the changes. And if we check now, we can see the new customer. In some databases like Postgres, read committed is the default isolation level. So make sure to always check your database isolation level and act accordingly. Let's demonstrate the non-repeatable read issue. This time, we will fetch the balance from the customer table where the ID equals 3. We get 200 as a result. So let's assume now we assign the customer to a specific category based on the balance they have. So what will happen if the second terminal updated the balance of this customer while we are still in the same transaction? We will set the balance to 1000 and commit the transaction. Back in the second terminal, we run the same query again, and this time we get a different value. This happens because the other transaction has modified the data in the meantime. When a transaction reads the same data twice and get different results due to external modification, this is known as non-repeatable read issue. To solve this issue, we will set our session to use the default MySQL isolation level, which is repeatable read. As before, we will select a new transaction and then select the balance of the customer. Switching to the terminal inside the Docker, we will update the customer balance to 500, then commit the transaction. If we switch back the terminal and trigger the query, we will still have the old value of 1000. So, if we run the same query multiple times within the same transaction, we should get consistent results. We will commit the changes and start another transaction. I will demonstrate the phantom reads issue even it doesn't happen inside MySQL. Let's get all customers with balance 500. For now, we get a single customer. Switching to Docker, we will update the customer balance to 500 where the ID is 1. We commit the changes and switch back to the other terminal. Since we are using MySQL, the phantom read issue is already solved within the repeatable reads isolation level. But if we tried the same scenario on Microsoft SQL Server, we would get 2 items instead, which means in that case, repeatable reads protected us from seeing updated values for already selected data. But the items in the result list itself would still differ between executions. Moving on to the last isolation level, the serializable, it is the most secured among all isolation levels but the least performant. Let's start a transaction, then select all customers. Switching to Docker, we will try to update the balance of customer 1 to 800. Notice the query didn't execute and still in progress. That's because when we select data in serializable mode, all selected records get locked to prevent skew writes. So if we commit the transaction, from Docker we can see the query finished executing as soon as the lock was released. Switching the terminal, let's try to get the customer with ID 1. This time, we are not able to retrieve data, since it's running in a serializable and the other transaction already updated the record but didn't commit yet. This happened to ensure we always read and write to the latest version of the record. So from Docker, we will commit the transaction, and switching back, now the fetch of the customer works fine. Lastly, we will try to update the balance for the customer with ID 3. It works fine, but if we try to update the value for customer 1, it waits until the other transaction either commit or rollback. So let's roll back this transaction and commit the transaction inside Docker. And we are done. Switching to the IDE, we will explore how to change the isolation level to the transactional annotation. We can open any class that has a transactional annotation, and then within the transactional annotation, we can set the isolation attribute. It has the default, where Spring follows the default database isolation level, or we can set it to serializable, read committed, read uncommitted, or repeatable read, just as we discovered. This is the last lecture in this course. Hopefully, you now have a better understanding how isolation levels impact transaction and data consistency. Also, you should be able to implement transactions in your own project.